Jupiter. Vast, mysterious. The largest planet in the solar system. Made almost entirely of gas, this violent world of 400-mile-an-hour winds and storms twice the size of Earth may also be the blueprint for how planets are formed. And on one of Jupiter's 4 largest moons may lie the answer to the most important question of all. Beneath these vast ice sheets, mankind could finally discover if alien life exists. Cutting-edge space missions are unlocking the secrets of this enigmatic giant, Jupiter. In the last 50 years, space missions have revealed worlds we never could have imagined. From the mountains of Mars to the methane lakes of Saturn. Yet one planet captures our imagination more than any other. The greatest of them all, Jupiter. Most of what we know about Jupiter comes from one mission, Galileo, launched aboard the Space Shuttle Atlantis in 1989. Each new discovery it makes deepens our understanding of Jupiter and its moons. It may also uncover evidence of how the solar system itself was formed. "11 times bigger than the Earth, yet probably without a solid surface. Jupiter is a ball of gas and liquid 90,000 miles across, with lightning superbolts 1,000 times more powerful than the strongest strikes on Earth. And a ring system like Saturn's, but too faint for our telescopes to see. The Great Red Spot, a single vast storm with 250-mile-an-hour winds. So huge, it could swallow the Earth 3 times over. 63 moons orbit this giant. Galileo will study 4 of them: Io, Europa, Ganymede, and Callisto.
Each of which would be a beautiful target for a space mission in and of itself.
Scientists expect dead and lifeless worlds 500 million miles from the Sun. Io, Jupiter's closest moon, is slightly larger than Earth's own moon. But Io is far from lifeless. Huge plumes of sulfur dioxide reach hundreds of miles into space.
Very peculiar surface with reds and yellows. Someone nicknamed it the pizza moon.
Ganymede, the largest moon, is a world of scars and frozen slush. And Europa, most mysterious of all. Its icy surface may hide a liquid ocean below. Where there's water, there could be life. A new generation of probes are set to explore the mysteries of the Jovian system. Juno, Europa Explorer, and the underwater probe, Endurance. 3 missions, 1 goal, to at last reveal the secrets of these alien worlds. Before Galileo, previous missions could only look from afar. In the 1970s and early 80s, Pioneer and Voyager gave us tantalizing glimpses of Jupiter and its moons, but they raised more questions than they answered. How did Jupiter form? What powers its vast storms? And why are its moons so geologically active? Before these questions can be answered, the team have to overcome a simple problem. Galileo is unable to carry enough fuel to reach its destination. NASA engineers need another way to get to Jupiter.
And they came up with a brilliant solution. We wouldn't go to Jupiter at all. We'd start by going to Venus.
By flying close to Venus, and then Earth, using a gravitational slingshot method, Galileo steals some energy from the planets to accelerate itself toward its final destination, Jupiter. When Galileo arrives after a journey of 6 years, a small subprobe will detach and plunge into the depths of Jupiter's atmosphere. It will have less than an hour to analyze its surroundings before being crushed by the extreme pressure. Everyone expects Galileo to beam back extraordinary information. As the spacecraft nears the end of its journey, it coincides with a massive comet on a collision course with Jupiter. Galileo is in an ideal position to watch. It could find clues to one of the most important questions about Jupiter's history. How was it made? Up until now, scientists believe that Jupiter is made from the leftovers from the birth of the Sun, a primordial planet frozen in time. If so, the Sun and Jupiter will have very similar chemical compositions. The comet's impact will stir up chemicals from below the surface, enabling the team to analyze them and see if the theory holds true. They are about to get more than they bargained for.
I just couldn't believe that we were going to get a chance to see one body in the solar system smash into another one.
We had an up-close and personal view of this unique event.
The comet's name is Shoemaker-Levy 9, or SL9. David Levy is part of the team that first discovers it.
This was going to be the first time that a comet collided with a planet, the first time in recorded history. And we had no idea what we were going to learn from it.
The day arrives. On mountaintops and in space, more telescopes are trained on the same part of the sky than ever before. Some scientists believe Jupiter's thick atmosphere will simply swallow the comet without a trace. Others hope the impact will dredge up matter from deep inside the planet, giving us vital clues to its composition.
We were talking about the largest, biggest planet in the solar system being hit by a tiny comet. Most scientists thought it would be a fizzle. Boy, were we lucky.
As the comet approaches, Jupiter's massive gravity tears it to pieces. Now, 20 separate fragments will strike the planet, some a mile or more across. Astronomers across the globe are about to witness something amazing.
Yeah, that's it.
One by one, the fragments hit. The largest releases as much energy as 300 million atomic bombs. A fireball shoots 2,000 miles above the top of Jupiter's clouds. Each fragment produces a separate impact cloud, visible as dark black bruises in Jupiter's southern hemisphere. They're the size of the Earth.
The first thing we saw with each impact was either the plume of dust and gas, as seen by either Galileo or the Hubble Space Telescope. The next thing we saw was the formation of the large jet black cloud all over Jupiter's southern hemisphere.
But the real surprise doesn't come from the clouds. It comes from the shock waves the impacts send through the upper atmosphere. There's only one explanation, and to astronomers, it's a revelation.
When Shoemaker-Levy 9 crashed into Jupiter, it's sort of like a rock going into a pool. It sent out waves, and the speed of the waves depends on the amount of water in the atmosphere. And the speed was faster than we thought, and so we inferred that there was more water than we had expected. You can sort of see it here. Well, you can see the ripples spreading out. And it was the speed at which the circles grew that told us there was more water than we expected.
The discovery is a surprise. It means that the composition of Jupiter is different from the Sun. It threatens to overturn everything scientists think they know about Jupiter's formation. A new theory is needed. In 17 months, Galileo will arrive and analyze Jupiter's chemistry firsthand. Only then can the team solve the mystery. 1 year after the comet SL9 strikes Jupiter, Galileo is on its final approach. There's a lot at stake. Scientists now know Jupiter may have 10 times more water than previously thought. If so, they may need to find a whole new explanation for how this strange world formed. Galileo's first task will be to directly measure the chemistry of Jupiter's atmosphere, including the amount of water. Galileo will release a small probe into Jupiter's clouds. The probe will also measure the wind speeds and temperatures at different depths to try and explain why the weather is so violent, as well as answering the big question: is Jupiter a long-lost cousin of the Sun, or something else entirely? As the probe dives into Jupiter's atmosphere, scientists are convinced they'll find the layer of water vapor the comet revealed, giving vital clues to the planet's creation.
And I even announced a prediction at a scientific meeting, offering to bet anyone in the audience $10 that the probe would find more than a certain amount of water.
But instead of water, the probe drifts through thin, wispy gases. It has flown into a downdraft, a dry gap in the clouds. Where is the water they were expecting to find? Jupiter must have both dry areas and wet spots. It's not what they expect.
What they discovered was that Jupiter has some long-term weather patterns, spots that move around that they didn't really realize were there before.
The Galileo team holds their breath. The probe dives deeper, but still there is almost no evidence of water. Less than an hour of data is about to trigger a revolution in our understanding of how the solar system formed. The probe does detect a high proportion of heavier elements like argon, krypton, carbon, and nitrogen. It finds levels 2 to 3 times higher than found in the Sun. These elements only condense at extremely low temperatures, lower than the temperature found at Jupiter's present position.
We learned that the atmosphere of Jupiter has chemical constituents that came in with very cold material from the outer solar system.
For astronomers, the discovery is a bombshell. The presence of these elements means Jupiter must have formed in a different way than the Sun.
This little probe, in one felt swoop, showed us that all of our ideas of how planets were formed were wrong. We didn't understand how the planets were made, and we didn't understand the early solar system.
The small probe's discoveries shocked the scientific community. Could the giant planet have formed further out in the solar system, where it's colder, then migrated into its current position? Or did comets or asteroids bring the heavy elements and water to it? After 58 minutes, and before the answers become clear, the probe falls silent, burning up in Jupiter's inner atmosphere. The probe has given scientists some remarkable insights into Jupiter, its atmosphere, and how it formed. But the big question goes unanswered. In 2011, a new mission, Juno, will attempt to find the answer. It will fly closer to Jupiter and gather more information than ever before. When Galileo's small probe plunged through Jupiter's atmosphere, it hit a dry spot. Just how much water Jupiter holds is still a mystery. Juno will take a different approach. Using the latest microwave technology, a radiometer, it will scan for water around the entire planet. Scientists hope that finding the missing data will finally solve the mystery of how Jupiter was formed.
What we're really after with Juno is the ingredients. From the ingredients of Jupiter, we're going to figure out the recipe. And that's what's going to tell us how planets are made.
With the probe having completed its work, it's now time for Galileo, 130,000 miles above Jupiter, to turn its attention to another long-standing mystery, the planet's weather. How can storms 3 times the size of Earth get so big and last for over 300 years? Jupiter's weather is a maelstrom of swirling clouds, lightning storms, and massive hurricane-like vortices. For the Galileo team, it's a mystery. On Earth, weather like this is powered by the heat of the sun, but Jupiter is 500 million miles away, so there must be some other source of power. Its most famous feature is the Great Red Spot, a storm whose clouds tower 5 miles above the atmosphere and plunge deep into a chemical soup below.
The red spot is red because of the chemicals that are trapped there in the center of the red spot have been baked and cooked by ultraviolet light and have turned red.
Astronomers have watched the Great Red Spot for at least 300 years. On Earth, even the biggest storms only last about 2 weeks. So how does the biggest storm in the solar system, 3 times wider than the Earth, get enough energy to rage unchecked for centuries? Scientists believe smaller thunderstorms could hold the answer. In order to solve the mystery, they had planned to video the Great Red Spot and other smaller storms in action. Understanding the mechanics of these turbulent weather systems, the Galileo team hoped to reveal the source of their power. With the high-gain antenna out of action, this simple solution won't be possible. The team back at Mission Control need a new approach.
Instead of making long, continuous movies, we made 3-step movies. You watch the red spot, you come back a few hours later, you watch it again, and so it's just a 3-step movie instead of a continuous movie.
Galileo homes in on a turbulent area of small white spots caused by what they think is convection or rapidly rising air. If these are storms, they will need to find proof. They need to locate another of Jupiter's most extraordinary features. Lightning bolts, 1,000 times more powerful than on Earth. But these are only visible at night.
Jupiter is 11 times bigger than the Earth. It's really big. If you look at this globe, you can see a few intense white-colored spots, small, intense white-colored spots. And when we got around behind Jupiter and looked at the night side, it was those very white-colored spots that had the lightning in them, and no place else. So that identified where the thunderstorms were.
Having identified the thunderstorms, the next step is to find out whether these small white spots can grow into larger ones. Galileo is in the right position at the right time.
There were some white ovals that formed in the 1930s, 3 of them, and they had been around for 60 years when suddenly 2 of them merged.
Galileo watches as 2 of the ovals merge to form a larger, more powerful storm. 2 years later, the 3rd oval also merges, forming one large storm in a belt below the Great Red Spot.
And then it had slowly turned red, so that it resembled the Great Red Spot, but not quite as big.
Nicknamed the Red Spot Junior, observations of its birth may also help to solve the mystery of where these large storms get their energy. Jupiter's storms are cannibalistic. They swallow smaller storms. This is how something as large as the Great Red Spot came into being.
It's like a food chain where the big fish eat the little fish and the little fish eat smaller fish. And the primary harvesters of energy on Jupiter are the little thunderstorms.
This accounts for the source of all the energy, but it doesn't explain why these vast storms last so long. Conditions on Jupiter are so turbulent that the storms should blow themselves apart. On Earth, vortices such as tornadoes soon die out, but on Jupiter, vortices last for years. Jupiter is the fastest spinning planet in the solar system, turning 22 times faster than Earth. Ironically, Scientist John Arno thinks this rapid spin explains the stability of Jupiter's storms.
In rapidly rotating systems, vortices can be long-lived. It's very surprising. Normally we would think they'd shred themselves. They never do. What we've learned from these missions is that it's very coherent, is that it's very stable.
When two different colored dyes are mixed in a rotating jar of water, the results are startling.
At first, what looks like it's going to be a mess quickly turns out not to be a mess. Instead, we generate two large-scale vortices that you'll see are going to be very long-lived and coherent. And this is the idea. In rotating fluid systems, when you try to mix them, instead of just destroying any dye signal or any signal in the fluid, you get large-scale structures, similar to a great red spot.
Galileo has revealed why some storms get so big and last so long. But scientists are still mystified by Jupiter's most distinguishable characteristic: its parallel red, white, and brown stripes. It was assumed that some colors are rising gases and others sinking. But Galileo finds this may not be true. Although its atmosphere is hundreds of miles deep, only the surface layer is visible. Here, high-velocity winds blow in opposite directions, causing these multicolored patterns to be dragged across the surface.
The colored bands are associated with vertical motion, and some of them are mapping out rising motion, and some of them mapping out sinking motion. It may be that the rising motion happens at one level, and the sinking motion happens at the same bands, but at a different level.
They won't find out until the Juno mission in 2011 looks through the top layer of Jupiter's atmosphere to see just how the planet is spinning.
Is it all spinning as one solid body like the Earth does? And what we see on the surface is just a bunch of clouds, a surface meteorological layer? Or is it inside a little bit like an onion, where there's different layers, and each layer is spinning in a different direction and at a different speed? We don't actually know that answer.
Juno will orbit Jupiter 32 times, each lasting 11 days. The orbits will pass over Jupiter's north and south poles, shifting longitude with every flyby to scan a new section of the planet. For the first time, Juno will map Jupiter's entire atmosphere down to a depth of 350 miles. Jupiter's vast weather systems may finally yield their secrets. Scientists now realize that the planet's fast rotation maintains Jupiter's long-lived storms, but more importantly, it also drives Jupiter's most powerful force, its magnetic field.
And we can study that system and compare it with what goes on at Earth and learn a lot that will help us understand Earth as well.
The Earth's magnetic field is generated by the churning motion of molten iron around the core. Jupiter is made of gas, but at its core, the hydrogen is so compressed, it acts like liquid metal.
The magnetic field is created deep down in the planet, where the pressures are so great that the hydrogen in Jupiter has become metallic. It actually behaves like a metal. And so it's moving around and currents are being created. And these manifest themselves out into the magnetic field that surrounds the planet.
The metallic hydrogen churning in Jupiter's core creates an incredibly powerful magnetic field around the planet. It stretches across the solar system to Saturn and beyond, holding in its grasp charged particles and gases.
It's enormous, 50 to 100 times Jupiter's size going across, and the tail is dragged out by the solar wind all the way back to Saturn's orbit.
Jupiter's magnetic field is the largest object in the solar system. If we could see it from Earth with the naked eye, it would appear larger than our moon. It's also strong enough to divert the constant stream of sulfur emitted from the huge volcanoes on Jupiter's closest moon, Io. This material also funnels down toward Jupiter's poles, creating a breathtaking light display. Like Earth, Jupiter has northern and southern lights, called auroras. For the first time, Juno will analyze the charged particles and magnetic fields that create these huge displays.
We're flying close, we'll dive underneath the radiation belts and out the other side. And we'll fly through the charged particles that bombard and light up the atmosphere with the northern aurora.
The team hopes the study of Jupiter will yield a better understanding of the dynamic processes that create Earth's own magnetic field. But the Jovian system has other secrets to offer. Its moons are not cold and inactive, but dynamic worlds that may hold the answer to the ultimate question: is there life beyond Earth? The Jovian system is immense. 63 moons orbit the planet, some large enough to be planets in their own right. They are also an enigma. Small planets and moons usually cool faster. So how can these moons be so hot and geologically active now? The answer may also contain a clue to the holy grail of science. Is there life on other worlds? The 4 largest moons are Ganymede, Callisto, Io, and Europa. Each one is profoundly different and holds incredible surprises.
Where every time Ganymede goes around once, Europa goes around twice, and Io goes around 4 times. It's not a coincidence. These moons have evolved into this wonderful cosmic dance.
Astronomers had expected Jupiter's moons to be cold, dead lumps of rock and ice. What Galileo finds are active, dynamic worlds. First stop, the mysterious Ganymede, the largest moon in the solar system. If it orbited the Sun instead of Jupiter, astronomers would call it a planet. These NASA images show its mountains, valleys, craters, and frozen lava flows. Almost immediately, the team finds something extraordinary. Galileo's magnetometer is picking up unexpected readings.
Now, I was flabbergasted. The evidence right there that there was a magnetic field caused me to say, I don't believe it.
Ganymede is the only moon in the solar system with its own magnetic field. But it's a puzzle. The moon should be frozen solid. If Ganymede's got a magnetic field, it must have a molten core.
People had thought that a body of the size of Ganymede would have cooled off so much in the 4 billion years that the solar system has been around that it would have been solid all the way through. So we had to change our view of the evolution of Ganymede.
The discovery of Ganymede's magnetic field only deepens the mystery of how planets form. Something must have happened in Ganymede's past, something catastrophic enough to have heated up this moon.
Galileo showed us that Ganymede is a fascinating world, one that's gone through a very complex history, a world in its own right.
But as well as detecting Ganymede's normal magnetic field, Galileo finds a second varying field.
That's telling us there's probably also a liquid water ocean within Ganymede.
Scientists suspect this ocean is buried deep beneath the moon's rocky crust. The team is eager to investigate, but Galileo's orbit means it must leave Ganymede and move on. More surprises await. Next, the outermost of Jupiter's 4 largest moons. Callisto has its own mysteries. It's cold and rocky. The oldest and most heavily cratered landscape in the solar system. Its surface is scarred with ancient meteorite impacts. Scientists are perplexed by craters with strange bright rims. It seems dark surface material has slipped away, exposing the lighter material below. Nothing like it has ever been seen on Earth.
So what's the material made of that's slumping down? What's the process that's causing it to slump off? And it certainly proved to be a much more interesting body upon close examination than we ever thought.
Although the surface is a chilly minus 279 degrees Fahrenheit, Galileo's data suggests that just like Ganymede, Callisto can't be frozen solid. It detects a very weak magnetic field, suggesting it too may have an ocean. But the data is confusing. Other instruments aboard Galileo suggest that 125 miles beneath its surface, Callisto consists of a mixture of rock, metal, and ice, right down to its core. It's another mystery. The standard theory of how moons and planets form says that they should heat up when the material they're made of first joins together. The heat should then separate the rock from the ice. Strangely, on Callisto, it hasn't.
That would mean it never got really hot in there. How do you make such a large moon and not have it heat up? We still don't really understand Callisto.
Like so much of the Jovian system, Callisto raises more questions than it answers. We don't know what's going on inside the moon. We don't even know what material covers its surface. The story of Jupiter's next moon is equally bizarre. Io is the same size as our moon and is the closest of Jupiter's 4 large moons. It is the most volcanically active body in the solar system, with over 400 volcanoes, up to 124 miles across.
If you could have a bird's eye view of Io, it would be really extraordinary. You would see these plumes that are hundreds of miles high, these enormous lava flows, and big lava lakes just boiling and bubbling away on the surface that is all really strange and has these colors of pepperoni pizza.
Volcanoes constantly reshape Io's surface. Galileo's pictures are totally different from the ones Voyager sent back some 20 years before. But how can a landscape change so dramatically in such a short space of time? Huge craters seem to come and go. The cause of their disappearance seems to be giant plumes of sulfur-rich gases shooting around 200 miles above the surface.
We concluded that it was the plumes that were depositing fine material on the surface and actually erasing these craters over long periods of time.
But as with Jupiter's other moons, there is a further mystery. This much volcanic activity requires an immense amount of heat. But where does it come from? Io, 500 million miles from the sun, should be too cold. But clearly it's not. Could the answer be gravity? Jupiter's gravitational field keeps Io in orbit, but as it goes around, it passes on the inside of Jupiter's other moons. Their gravity pulls Io in the opposite direction. That distorts Io's shape. It's the distortion that creates the heat.
As Jupiter's large moons orbit around the planet, they're pulled and pushed and squeezed as they go around in their orbits. And this creates heat, friction, and causes melting within Io of the rock to power its volcanoes.
It raises tides on Io, very much like the moon raises tides on the oceans on Earth. Only on Io, the whole surface goes up by over 300 feet. Can you imagine what it would be like on Earth, like here in Los Angeles, if the crust of the Earth was rising 300 feet?
It's an astonishing discovery. A world shaped by forces so violent, it's pulled apart like taffy. Yet amazing as it sounds, of all Jupiter's moons, Io may not be the strangest. The next moon on Galileo's path, Europa. Its surface is covered in strange geological shapes and parallel tracks that cut across the ice. It's an ice world with an extraordinary secret. Could it harbor the ingredients for life? Images of Jupiter's moon Europa from earlier missions reveal a pinkish-white world. But Galileo finds fewer meteor craters than expected. That means something is erasing the craters after they form. Because Europa's surface is ice, scientists believe water could be welling up from below. This moon is so intriguing the team wants a better look. But to do so means spending more time at Europa than planned.
The original schedule called for only 3 flybys of the moon Europa, but the evidence was so compelling that it compelled the mission to be extended in length and to go back several more times.
Galileo's first job is to image the moon in greater detail. The question is, how active is Europa's surface? Are the processes that erase impact craters fast or glacially slow? The team begins by assuming the process could take billions of years. That changes fast.
I'm listening to them discussing the age of Europa's surface dropping. Oh, well, maybe it's a couple billion years old. And then the next flyby, well, it might even be 100,000 years old. And then the next flyby, it may be currently active.
While measuring Europa's magnetic field, Galileo uncovers another mystery. As the moon orbits Jupiter, its magnetic field shifts. Europa must have a conductive layer which allows Jupiter's magnetic field to pass through it. There is only one thing that could cause this, and it's a big surprise for the Galileo team.
We were able to interpret these signatures as being produced by a global ocean beneath the surface of the ice.
Scientists believe Europa's ocean is vast. It covers the whole globe to a depth of 100 miles, making it the largest body of liquid water in the solar system. If so, the team must first address a fundamental problem. Europa's surface temperature can reach -200 degrees Fahrenheit. Why doesn't such a huge ocean so far from the sun freeze? Astronomers think the answer may be the same one that drives the volcanoes on Io. Jupiter's gravity stretches and compresses the moon, creating heat within. It's the heat that keeps the surface in constant motion. This could also explain some unusual features found on Europa.
Galileo images showed that ridges crisscross the surface of Europa. These are bizarre features that travel across the surface for up to 1,000 kilometers, and typically in pairs. That is, a ridge with a depression in the middle and another ridge. These are bizarre features like nothing we see on the Earth.
At first, these ridges are a puzzle, but researchers soon come up with a solution. Planetary scientist Bob Pappalardo reproduces the effect with ice blocks in the lab.
As Europa is flexed by Jupiter's gravity, its surface bends and cracks and makes fractures through the ice. Well, as it's squeezed and bent, the ice slides back and forth along these fractures. Now this can create heat as these blocks move by one another. And that heat can warm the ice on either side of the block, and that warm ice rises up to form these strange ridges that we see, these tracks that seem to go across the tundra of Europa.
Galileo reveals a world in constant motion, evidence of heat hidden below the ice. Flows of material on the surface are possible evidence of ice volcanoes or geysers. Brown-red stains stretch across the ice where it has cracked open, and salty material from the interior has welled up from below.
We see pits and spots and domes on the surface of Europa that might be related to the rise of blobs of warm ice that move up through the shell, sort of like a lava lamp.
Heat from the interior of the moon may even drive hydrothermal vents in the ocean. On Earth, hydrothermal vents on the seafloor are hotspots for life. Galileo's data also suggests there's carbon dioxide frozen on Europa's surface, possibly welling up from the ocean below. If so, the find is huge, because CO2 is vital for life. Does this mean there's life on Europa?
I'm in the camp that where there's water, there's a very good chance that there's life, and where there's materials for that life to use. And on Europa, we seem to have the materials and we have the water.
If we search and find life within the ocean of Europa, that'll be an enormous leap in understanding whether we're alone in the universe or whether life may be everywhere.
The search for life is an irresistible lure. Scientists are desperate to go back to Europa, and near the end of the next decade, they hope to launch a groundbreaking mission to orbit the moon. The Europa Explorer will take the first steps toward answering the biggest question of all. Is there life on other worlds? It will survey the ice on Europa's surface. As well as analyzing its structure, it will search for spots where we could one day break through to the ocean beneath.
We need to measure the gravity in detail. We need to do radar studies. We need to look at the surface composition. We need to understand the geology. We need to understand that tidal flexing that heats the interior and causes that thick layer of ice to flex with the tidal forces.
The Explorer's main tool is radar. It will give scientists a 3D map of Europa's crust. This will tell them just how thick the icy shell is.
How far beneath the surface the ocean is, if it's a global ocean, how deep it is, how thick the ocean layer is.
These are crucial questions. Once scientists know how thick the ice is, the next step is to work out how to get beneath it, and that will mean a completely new mission. A probe that will not only orbit Europa, but land and explore its subsurface ocean. Endurance is already at work in Antarctica. A robotic submarine. It's the first of a new breed of underwater probes that can also operate under the ice. The aim is to create a vehicle that needs no instructions from home. Endurance must make decisions all by itself.
Every vehicle we've sent to space so far has the ability to talk back to Earth, get commands from Earth, and have people in the loop. This will be a whole new ballgame, and it's something that we're going to be able to test in Antarctica.
Endurance is currently investigating a lake hidden under nearly 15 feet of ice in Antarctica. Perhaps one day, a vehicle like this will search for life on Europa. But first, it has to get through the ice.
That thick ice cover, it takes a lot of energy to melt ice. People don't usually appreciate that, but we'll need some kind of nuclear system that will melt that ice, and it will take weeks, perhaps months, to get through that ice.
We might imagine a lander spacecraft that melts its way all the way down to the ocean and explores what's really down there.
The discovery of life on another world would be one of the greatest finds of all time.
We're not talking about fish or whales or the Loch Ness Monster. We're talking about microbes. Could there be tiny single-celled organisms within the ocean of Europa?
I mean, if you just find bacteria, it would be fascinating. But who knows? You know, maybe there's something more sophisticated, there's something swimming around. Who knows?
Even the simplest life forms would have profound implications.
If life exists in the ocean of Europa, that would tell us that life probably exists almost anywhere there's a water-rich environment. That would be an amazing discovery.
Jupiter and its moons have already transformed our understanding of our place in the solar system. Now, new missions to Europa may finally prove that life on Earth is not unique. And if there's life on two worlds, then why not on many? Jupiter and its moons may one day give us hope. We will find not just life, but intelligence out among the stars. Diamonds, 4 billion years old, and they still dazzle us. But these rocks aren't just for show anymore. Hidden inside are powers that could change your life.
The future of diamond is very exciting and opens up what many of us have been calling the new diamond age.
To reach that shining future, scientists have to outdo nature and build a better diamond.
The new synthetic diamonds, that's a technology that's going to take us places we've never been before.
It's a dazzling challenge. Can science do the unnatural and make a super diamond? Diamonds are like no other substance. They're 4 times harder than any mineral on the planet. They resist corrosion. The best are completely transparent. And they conduct heat. Some can conduct electricity.
What you have is a material such as diamond that has a fantastic range of unique properties, and it's the combination of these unique properties that makes diamonds special.
If science can harness the powers of these stones, it could revolutionize our lives. From the microchips in our phones to the machines that explore space.
They'd be super durable, they'd last forever. They'd be resistant to heat and cold and the other kinds of extremes.
It's said diamonds are forever, but they aren't. Most contain natural flaws, flaws that can't withstand extreme heat and pressure. To transform technology, science must do something unnatural. Create the ultimate diamond in the lab.
Nature is the guideline, and the question is, can we improve upon it? The race now is to produce a super diamond.
A super diamond would have all the properties of a natural diamond, but could be manufactured in any shape or size. Most of all, they would mimic the properties of the rarest gems, like this one. The Hope Diamond. Perhaps the world's most perfect natural diamond. It's kept behind bomb-proof glass in the Smithsonian Institution in Washington, D.C. At 45.5 carats, this gem is over 100 times bigger than the average diamond ring. It's one of the largest and most valuable diamonds ever discovered, worth around $250 million. But that's not all. This gem has some unusual properties that highlight what makes diamonds so special. Jeffrey Post, the curator of the National Gem Collection, is researching this stone. In the lab, he demonstrates a phenomenon that sets the Hope Diamond apart from most others.
We can take an ultraviolet light And we can expose the Hope diamond to the ultraviolet light, and we'll leave it on for about 10 or 15 seconds. Also notice that one of the white diamonds on the outside fluoresces very bright blue. And so now we're going to turn the room lights off, and I'll turn off the ultraviolet light, and we can see the intense orange glow, the property called phosphorescence.
For years, this glow was attributed to a curse cast over the diamond when it was stolen from an Indian temple centuries ago. But Post isn't superstitious.
So here you've got supposedly a cursed diamond that glows this blood red color. Well, you know, that's a great story in itself. But then the scientist in many of us says, well, why does it do that?
Post and his team investigate using a spectrometer, an instrument that analyzes wavelengths of light. The spectrometer shows that the Hope's distinct hue comes from two colors: aqua and red. The team can now identify two chemical elements in the diamond: boron and nitrogen.
Suddenly, now I understand what is going on when this diamond is phosphorescent.
Boron makes the stone blue. When combined with nitrogen, the stone shines red. Chemicals, not a curse, make the Hope glow. It's not the red glow that excites scientists, but the element that makes the Hope blue: boron. Boron does more than color diamonds. It also allows them to conduct electricity.
Blue diamonds, because of the boron present in them, are in fact semiconductors of electricity, which makes them very different than other diamonds that are pure carbon.
Pure white diamonds are electrical insulators. Try to pass a current through them, and nothing happens. But blue boron-rich diamonds, like the Hope, are electrical conductors. The extra atoms of boron interact with the existing diamond atoms, letting an electrical current pass through. But all diamonds, not just blue diamonds, have another useful property. They transfer heat better than any material known. If science could make synthetic diamonds that both conduct electricity and transfer heat, they could revolutionize a critical component of daily life: the semiconductor. Semiconductors are the vital component in nearly every electronic device. In transmitting electricity to the precision control of microchip technology. For the past 50 years, these devices have been made almost exclusively from silicon. But silicon has a major drawback. The more electricity it carries, the hotter it gets. The result? Most silicon chips require complex cooling technology. If they exceed about 300 degrees Fahrenheit, they'll shut down.
One of the huge hurdles that are facing manufacturers is that they have to be able to remove the heat away from these electronic systems. You know, think of your own laptop at home as you're operating it. It gets hot. And so this becomes a big problem. Right now they're using metals mostly to do that. But diamonds, in fact, are much better conductors of heat than metals are.
With the discovery that blue diamonds transfer heat and conduct electricity, scientists can imagine the unimaginable. A world beyond silicon. A world where everything from your cell phone to a spacecraft runs on diamonds. Diamonds can carry 30 times more power than silicon and operate 3 times faster. And they're so efficient at transferring heat, they could run a computer at speeds that would melt a silicon chip. They also resist temperatures over 1,800 degrees Fahrenheit.
To be able to coat electronics with diamond or use pieces of diamond as the heat sinks would certainly offer a whole new direction for the manufacture of even smaller, more powerful electronic devices.
Despite their eye-catching sparkle, diamond's real potential has been overlooked for centuries. The possibilities for technology are almost endless. But there's one problem. Diamonds are rare and expensive. Natural semiconducting diamonds like the Hope are thousands of times more rare. And they don't come in the right shape or size for industrial use. So scientists are trying to create a synthetic super diamond with all the powers of a natural blue diamond, but in a size and shape of our design. To succeed in creating a super diamond, scientists must first discover how nature made hers. And for the answer, they look to the stars. For scientists to create a synthetic super diamond, they must first get back to basics and investigate the ingredients of a natural diamond. For all their rarity, diamonds are made from one of the most familiar elements on Earth, carbon. Carbon is so fundamental, it forms the basis of everything around us. Even we are 18% carbon. It's so common, it's estimated that our planet contains over 100 billion tons of it. But carbon doesn't originate on Earth. It comes from long ago and far away. A star on the brink of death. A red giant. Astrophysicist Neil deGrasse Tyson studies carbon's dramatic formation.
Well, the universe is born without any carbon. Our sort of birth ingredients are hydrogen and helium and just trace amounts of lithium. So carbon comes later. Carbon is forged in the cores of stars.
This red giant star once looked like our sun. But as it ages, it grows over 1,000 times bigger. Instead of glowing white hot, it glows red as it reaches the end of its life. It's running out of fuel. Its core is now composed almost completely of helium. In its death throes, a nuclear reaction in the core breaks down helium and fuses it together in a new configuration, carbon. Dying red giants are the universe's carbon factories. Eventually, the star explodes in a white-hot flash, so strong that billions of tons of carbon are flung out into the farthest reaches of space.
What happens is the star collapses, and the entire core, in response to this collapse, rebounds and explodes. A titanic explosion we call a supernova. And its guts are scattered everywhere. And it's a spectacle. It's so much of a spectacle that you can see these stars explode halfway across the universe.
In time, the vast cloud of debris from the explosion is pulled into orbit around a new star. As this debris spins, it clumps together. Over millions of years, these clumps grow, and planets begin to form. This is how our solar system and our planet itself was born. And it's why Earth holds the raw ingredient for diamonds, buried deep in huge quantities: carbon. For scientists hoping to create a super diamond, a problem. The form carbon usually takes is weak. Carbon in its most familiar form is graphite. Great for pencils, but far too soft for high-tech products. Bob Hazen, research scientist at Washington, D.C.'s Carnegie Institution, is an expert on carbon and diamond formation.
You know, it's amazing. Diamond and graphite are made out of the same element, carbon, but they're so vastly different. Graphite has these planes of weakness, and you can see how every one of these black dots, the carbon atoms, are connected to 3 other carbon atoms in a triangle. But in diamond, every carbon atom is now connected to 4 adjacent, and this trellis, this network, this lattice. So diamond is strong in every direction. That's the difference.
For scientists hoping to create a super diamond, making it hard will be tough. They have to recreate a diamond's lattice-like structure. To do that, they have to figure out how nature turns basic carbon into a dazzling diamond. Scientists are on a quest to figure out how to make a super diamond. Their search begins here, South Africa, diamond capital of the world. Diamonds were discovered in these rocks in the 19th century. Hundreds of thousands have been mined here, but only recently did scientists learn how they actually formed. Professor Steve Haggerty is an expert on how diamonds are created.
Diamonds were a real mystery in terms of their origin. They were found in clusters. So you found one diamond, and by golly, there would be others to be found as well. So that led to the notion that the process in which the diamonds were brought to the surface was possibly deep.
Diamonds form deep within the Earth in an area called the mantle, the layer between the Earth's crust and its superheated core. Down here, intense pressure changes the molecular structure of carbon by crushing its atoms together and forcing them into a new lattice-like structure. Under extreme pressure and temperatures, carbon becomes diamonds.
The temperatures have to reach about 1500 degrees centigrade and the pressures about 50 kilobars.
That's 2,700 degrees Fahrenheit and the weight of over 4,000 grown men standing on your foot. The journey from a dying star to a diamond mine is almost complete. 100 miles still remain between their source in the mantle and the Earth's surface. Luckily, they're fast-tracked to the surface by a substance called kimberlite.
Kimberlite is a rock, it's the host rock to diamonds. Even though the diamonds do not form in the rock, it's the transporter.
Kimberlite is a volcanic rock that forms deep within the Earth. As it moves to the surface, it creates a carrot-shaped pipe filled with molten rock, mantle fragments, and diamonds. When it breaks through the crust, it erupts in small but violent volcanoes.
I like to think of these as volcanoes of opportunity. These rows, they picked up the diamonds from their safe deposit boxes deep in the earth about 200 kilometers down, and then were explosively erupted.
At the surface, magma builds up a mound of volcanic material that eventually cools and hardens. Hidden within the rock are diamonds, incredibly rare, perfectly formed crystals surrounded by kimberlite. Rarer still are blue boron-rich diamonds, like the Hope. Less than 1 in 100,000 form this way. "4 billion years from a dying star to the Earth's surface. Yet in a matter of days, scientists aim to turn raw carbon into super diamonds."
In order to produce anything of that nature, it would require extraordinarily high temperatures and pressures. It turns out that it's not very easy to transform graphite into diamond.
The attempt began in the 1950s, when General Electric launched Project Superpressure. Their goal, to create the first synthetic diamond. They developed machines to crush graphite at nearly 800,000 pounds per square inch and heat it above 2,500 degrees Fahrenheit, replicating the very forces in the Earth's mantle. It takes 5 years and millions of dollars, but finally, in February 1955, GE announces they've done it. The world's first synthetic industrial diamond. Over 50 years later, just outside Johannesburg, South Africa, a lab called Element 6 continues the quest for synthetic diamonds. Following GE's lead, they synthesize diamonds on a mass scale, not for jewelry, but for heavy industry. Scientist Richard Botkin is a pioneer of industrial diamond research.
We have banks and banks of presses that are capable of producing diamonds in no fewer than 45 minutes. To see such technology room after room is absolutely amazing.
The diamonds they produce start as a highly pure form of graphite powder. It's baked inside a pressure chamber between 2,500 and 3,600 degrees Fahrenheit.
Effectively, you're stacking 20 sedan motor cars on it and heating it between 1,400 and 2,000 degrees Celsius.
The result is a diamond 50% harder than those found in nature. And Element 6 can produce handfuls. These diamonds have revolutionized the drilling and mining industries. The friction from drilling into hard rocks, like granite, generates high temperatures that can damage ordinary drills. But diamond tip drills transmit heat away from the drill tip.
Oil and gas drilling benefits immensely from diamonds simply because we can drill faster and deeper with diamonds.
One shortcoming: industrial diamonds are small. The next challenge is to create diamonds large enough to be printed with circuit boards or shaped into other high-tech devices. It's a challenge that the Sarasota, Florida company Gemesis is tackling. Using a special machine, they actually grow large diamonds. They start with a seed, a microscopic diamond, either natural or artificial, and surround it with graphite. It's a delicate process that shows how hard it is to create large diamonds. In charge of the process is Chief Operating Officer Clark McEwen.
We take graphite and we put it along with an actual diamond seed into an environment that emulates what happens within the Earth.
These two forms of carbon, the diamond seed and the graphite, are placed inside the chamber, where they're heated and crushed by a powerful hydraulic press.
As you apply that temperature and pressure, what happens is that graphite turns into individual carbon atoms. And those atoms permeate down and it finds that diamond seed and it attaches to it. It acts as a template.
As the graphite melts, it releases carbon atoms, which crystallize on top of the diamond seed. Molecule by molecule, the diamond grows. What nature does in 4 billion years, they do in 4 days. The result? A large artificial gem, up to 3 times larger than the seed. With this breakthrough, scientists can now consistently make large diamonds. But the real breakthrough that scientists need is yet to come. Gemicists can't grow diamonds in the shapes needed for high-tech use.
We haven't gotten there yet, but we're constantly working on improving the process and making larger and better quality diamonds.
Scientists are trying to create a large diamond with all the properties of a real diamond, but in shapes and sizes not found in nature. From circuit boards to scalpel blades, the uses could be endless. As scientists struggle to perfect the diamond, a clue hurtles toward Earth from an unlikely place. After years of research, scientists discovered how to make gem-sized diamonds. One hurdle remains to making a true super diamond, making them in any shape and size. Science needs a breakthrough, and it comes from space. These strange objects look like burnt stones. They've been found in South America and Central Africa. Tests reveal a surprise. The stones are actually diamonds. Black diamonds.
These are 2 of the famous black diamonds called carbonado because of their similarity to charcoal.
Carbonado has been known for centuries, but how it forms remains a mystery. Only recently has its potential value to science emerged. George Harlow of the American Museum of Natural History is investigating what makes carbonado so special.
Carbonado is a conundrum because it doesn't have the characteristics that we associate with diamonds that formed in the mantle on Earth.
Diamonds originating in Earth's mantle form under immense pressure and high temperature, so they're compact and dense. Not black diamonds. Using a microscope, scientists find they're riddled with holes.
It's got a lot of void space in it. Now, deep within the Earth, the void would have to be filled with something. Well, the something ain't there.
Normal diamonds contain very little void space. As they form deep in the Earth, they're crushed into a single crystal. Carbonado seems to form differently. Unlike normal diamonds, it's composed not of one crystal, but millions, all linked together. Scientists conclude carbonado formed not under high pressure, like normal diamonds, but low pressure. But just where does carbonado come from? Once again, research leads to the last gasp of a dying red giant.
The current theory for the origin and genesis of carbonado is that the small diamonds formed in supernova explosions.
Haggerty believes the vacuum of space explains Carbonado's unique structure.
The diamonds were hot, one diamond bashing into the other, and they finally became glued to form a larger diamond.
During its explosive formation, specks of mineral dust are also trapped, making the large diamond appear black. The diamonds are then transported to Earth by a meteorite.
When the meteorite hit, it showered diamonds, so this must have been a truly amazing sight, with Carbonado diamonds being liberated from the meteorite on impact.
It's not just the large size of space diamonds that fascinates scientists. Carbonado has another advantage over regular diamonds. Its multi-crystal structure makes it not only larger, but tougher. It's almost impossible to cut. Not so a natural diamond. Although it's one of the hardest materials known, it has its weaknesses.
You know, diamond's incredibly hard, but it can be broken along certain planes. They're called cleavage planes. And it just happens that there's certain directions in diamond where there are fewer strong bonds, and that's the direction the diamond opens.
A natural single crystal diamond will split cleanly where its chemical bonds are weakest. By following this cleavage plane, a gem cutter can split the stone perfectly. For scientists, this weakness in single crystal diamonds is a fatal flaw. Diamonds that might fracture aren't durable enough for high-tech use. The key to making a tough super diamond lies in replicating Carbonado's multi-crystal structure. Their theory of how Carbonado forms in the vacuum of space yields another breakthrough. A whole new way to make diamonds.
The space diamonds have now taught us that, in fact, we don't need pressure at all. This can be done in a vacuum.
Carbonado sets the stage for a new kind of super diamond. One tougher and larger than ever. That can be made into multi-crystal shapes not found in nature. The key is using low pressure to simulate the vacuum of space.
How do you make a diamond in a vacuum when diamond's only stable at high pressure? And the way you do it is by fooling the carbons into being so energetic, so excited, that when you cool them down, they find a more stable configuration. And the first one they find is diamond. And they don't go any farther.
This process is called chemical vapor deposition, CVD for short. It begins with a tiny diamond seed sealed inside a vacuum chamber slightly below atmospheric pressure. The chamber is heated to 3,600 degrees Fahrenheit. Then methane, a carbon-bearing gas, is pumped in. Then hydrogen. The gases are bombarded with microwaves, which agitates them, forcing the hydrogen and methane molecules to collide. This process releases a cloud of carbon atoms that settle on the seed, and gradually, the diamond grows. This was the seed they started with. 24 hours later, it doubles in size. At the U.S. Naval Research Laboratory in Washington, D.C., James Butler is taking this CVD process to the next level. They're growing not single stones, but wafer-thin diamond sheets.
One of the materials we grow starts with a non-diamond material, for example, a silicon wafer, onto which we put a very thin layer of these little diamond seeds. Think about shaking salt onto the kitchen table and having a whole bunch of salt crystals there. And then we put them in the CVD environment and they will grow. And as they grow together, they bump into each other and they become this mass. So it's all diamond, but with many different grains of different orientations.
Each diamond crystal bonds to another to form a mesh of crystals across the wafer, less than a 50th of an inch thick. They can be made up to 8 inches wide. The shape of the template determines the shape of the diamond sheet. Perfect for making a wafer to replicate silicon. They're much tougher than natural diamonds. They conduct electricity and resist extreme heat. These are true super diamonds. Super diamonds have been filmed with image intensifiers that show how much more efficient diamonds are at conducting heat than the copper traditionally used in electronic components. The left plate is made of synthetic diamond. On the right, copper. The two plates are placed in ice and attached to a thermal image intensifier, which records heat as it travels through an object. As the diamond plate on the left shows, it conducts heat faster than copper, up to 5 times faster. It's this unparalleled quality that puts the super in super diamond. Scientists are excited. For the first time, they have a material that could challenge the domination of silicon. Microchips made from diamond wafers can run electronic devices at higher speeds and with more power without overheating. Faster, smaller, and more efficient. Razor-thin computers, long-lasting cell phones, and picture-perfect TV screens.
I think the future of diamond is very exciting. Particularly, I think CVD diamond opens up what many of us have been calling the new diamond age.
Electronics are only the beginning. Today, scientists can make diamonds in shapes and sizes for uses that could revolutionize tomorrow. Researchers at the Carnegie Institution in Washington are trying to solve some of science's biggest mysteries. From how compressed gas can conduct electricity to how microscopic life can survive in extreme conditions. These investigations need extremely high pressures, which they create using a powerful vise called a diamond anvil cell. It squeezes an object between 2 diamond tips, creating a tiny environment of high pressure between them. It can recreate forces as extreme as pressure in the center of the Earth. For the Carnegie team's experiments, this wasn't extreme enough. But when they pushed the pressure higher, they hit a snag. The diamond shattered. Russ Hemley, director of the Geophysical Lab, decided to upgrade the anvil by making an ultra-hard super diamond.
Well, our group has been very interested in using diamond for high-pressure experiments for many, many years. And we basically needed to take this to the next level. We needed better diamond, stronger diamond, larger diamond than could be provided by Mother Earth or from conventional processes.
To create his super diamond, Hemley used a version of the CVD method to speed up the growth rate. The team then exposed the crystals to a high-pressure, high-temperature treatment to further harden them. The result? Another leap forward for super diamonds. The diamond not only grew many times faster, it also grew bigger. 15 carats. In just 6 days, they'd created a stone 1/3 the size and 50% stronger than the Hope Diamond. A gem that took nature billions of years to forge. The new super diamond was so tough, it broke Hemley's hardness gauge. When used in the diamond anvil, this new super diamond proved the breakthrough he needed.
This can produce pressures that are millions of times the pressures found at the surface of our planet.
Now, he can simulate forces so extreme they've never been studied before. Like those deep in the Earth's mantle, where pressures reach up to 1,300 kilobars. That's nearly 20 million pounds per square inch. This improved instrument lets Hemley study some of our biggest questions, like is there life in outer space? Hemley's team takes 2 common strains of bacteria, including E. coli. They place them in a liquid and crank up the super diamond anvil. The liquid turns into a dense form of ice. Under the intense pressure, most of the bacteria are destroyed. But incredibly, 1% survive. If bacteria can survive these harsh conditions, maybe life exists in outer space, perhaps on other planets. Thanks to super diamonds created under low pressure, diamonds will reshape the future. Super diamonds will change communications everywhere, especially on the battlefield. In constant use and battered by the elements, equipment like radios often break down in the harsh conditions of combat. But imagine if they were made of super diamonds. Already, they can be shaped into tiny sound transmitters called nanoresonators, making vital radios and computers more robust and efficient. They can vibrate up to 100 billion times per second to create the highest quality sound yet achieved. Yet, they're tough as nails. All this from a diamond 1,000 times smaller than the width of a human hair. It's not just soldiers who will benefit. Diamond resonators will eventually be used in everyday devices like cell phones, allowing longer talk time and crystal clear reception. The same sparkle that attracts us to diamond jewelry reveals another of its secrets, its clarity.
It's transparent to light. It slows down light that passes through it.
As light enters a diamond, the dense carbon structure slows it down to less than half its normal speed. As it reflects inside the stone, the light appears to hang around longer.
You can actually force light to completely internally reflect and come out at some other angle. That's why diamonds look radiant, because light comes in from one direction, comes out another. It makes you think it's generating its own light, but it's not. All it did was redistribute the light coming in from other angles. It's remarkable.
Now you know why diamonds sparkle. The unique optical clarity of diamond, the perfect material for high-tech optical uses. Diamond is transparent across a huge spectrum of light, from ultraviolet to infrared. It's the only substance through which light passes virtually unaltered. From super diamonds NASA can make super hard, super clear windows. The possibilities for super diamonds are endless. Soon, you may find a diamond everywhere, from your desk to your galaxy.
The future of diamond, we're just seeing the very beginning of it, and I mean the stars are the limit when it comes to what we're going to be able to do with diamond in the future.
Nature took billions of years to perfect the diamond. Now, we make super diamonds in days. Tougher, bigger, and better.
The new synthetic diamonds, that's a technology that's going to take us places we've never been before. It's going to take science in new directions. It's going to allow us to do things we could never do before. So the natural diamond, we treasure that as an object. The synthetic diamond, that will give us knowledge.
Like steel, transistors, and silicon, synthetic diamonds could revolutionize life. Welcome to the age of super diamonds. Venus, Earth's evil twin. Its clouds made of battery acid. At 900 degrees, its surface hot enough to melt lead.
Venus is pretty much like the biblical vision of hell today.
This may be the most hostile real estate in the solar system. Yet billions of years ago, Venus looked a lot like Earth. Why it changed, nobody knows. A new probe is on a mission to find out. What turned Venus from a promising Eden into an infernal wasteland? And is Earth destined to end up like Venus? November 9th, 2005. A Russian Soyuz rocket launches from Kazakhstan, carrying a tiny European spacecraft called Venus Express. Its mission, to travel the 250 million miles to Venus and find out why the planet evolved so differently from Earth. For centuries, Venus's surface remained an enigma, obscured by layers of dense clouds. Because Venus is closer to the Sun than Earth, scientists assumed it would be hot and humid. Some even imagined a tropical paradise. The perfect hothouse for life.
Venus should be about the same temperature as the Earth. And that's what we thought back in the 50s and early 60s. We thought Venus should be like Miami, Florida.
What was really going on beneath the clouds? In the 1960s and 70s, while NASA explored Mars, the Soviet Union launched a probe to Venus. Codenamed Venera, the craft beamed back the first images of the planet's surface. Not a tropical paradise, but a hostile desert. Lots of dust and no water. Venus resembles its twin Earth in many ways. Similar in size and composition, they were probably formed from the same cloud of gas over 4 billion years ago. But unlike Earth, 85% of its surface is made up of extinct volcanoes and solidified lava. The clouds are composed of deadly sulfuric acid. Atmospheric pressure is 90 times greater than on Earth, enough to crush a car. But the biggest surprise is temperature. The atmosphere is nearly all carbon dioxide. As on Earth, this gas acts like glass in a greenhouse, admitting light, but trapping heat. On Earth, increasing levels of carbon dioxide are raising temperatures a few degrees. But on Venus, the greenhouse effect has pushed temperatures through the ceiling to levels hot enough to melt lead.
We get there to find out that it's 900 degrees Fahrenheit, and it was very shocking.
The surface is so hot, rocks glow in the dark. Venus would disorient a visitor from Earth. Under permanent cloud cover, you'd lose your bearings. No stars, no sun, no shadows. To find out how these two identical twins, Venus and Earth, grew to be so different, Venus Express carries state-of-the-art instruments designed to unlock the planet's secrets. But the spacecraft's first challenge is just getting there in one piece. 5 months and 250 million miles later, the spacecraft nears Venus and the most dangerous stage. To achieve orbit will take perfect speed and timing.
Space is never really safe. There's always something that can go wrong, and you have to kind of provide for contingencies for that.
Too fast, and Venus Express will fly off into endless space. Too slow, and the planet's gravitational pull will bring it crashing to the surface.
The actual day of arrival, you have about an hour and a half that it's really kind of tricky. You want to make sure that you hit the right spot relative to Venus and that you're bending around Venus the right way.
To get into orbit, Venus Express must reduce speed by 3,000 miles an hour. April 11th, 2006. The engine fires to slow down the craft. For 10 minutes, Venus Express vanishes behind the planet. If it fails to achieve orbit, it's lost. No second chances. A 4-year mission hangs on hitting the brakes just right.
The most critical maneuver is happening out of sight and out of sound from the Earth. So it's a very harrowing time because you do lose communications for 10 minutes and everybody's on pins and needles to see what happens.
At 9:57 a.m., Venus Express transmits a signal to Earth. The spacecraft's pioneering orbit begins. A multi-million-dollar quest to unlock Venus's secrets. But first, it has to get closer. On an elliptical course around the planet's poles, the craft drops down from 40,000 miles above the surface to just 155 miles. Now, the work begins. The technology on board is a quantum leap forward from the last mission to Venus in 1990. Before, a probe couldn't analyze Venus's surface without landing. All the probes had a short life, crushed by the pressure, melted by the heat, and corroded by the acid. With this mission, scientists have found a way to study the surface without landing and keep their probe safe. Venus Express views the planet using infrared, a wavelength not visible to the human eye. Unlike visible light, the infrared can penetrate areas of cloud that are less dense, allowing the probe to peer through the clouds to the clear atmosphere below. Now, for the first time, scientists can reveal Venus in 3D from the ground up.
With Venus, when you look with a visible eye, you're limited to the very top 1% of the atmosphere. The upper regions, you see these hazes. When you get the ability to look with the infrared light, it allows you to pierce right through all these hazes and see down much lower into the atmosphere. In fact, you can go to the surface.
From 155 miles up, scientists will exploit these infrared windows to map the surface in detail never before seen. Their map will document exactly how Venus and Earth differ. Then, they hope to find out why. Despite decades of exploration, our sister planet can still surprise us. And soon, Venus Express makes a stunning discovery. A spacecraft orbits Venus on a mission to solve a mystery. Venus should be like Earth. But billions of years ago, our twin went its own way and evolved into the burning rock it is today. While studying the outer edge of the atmosphere, Venus Express discovers the first clue to what went wrong. It detects particles escaping into space, mainly helium, hydrogen, and oxygen. Hydrogen and oxygen make water. For years, scientists debated whether Venus's atmosphere held any water. Some argued if early Earth had water, so did Venus. Perhaps enough to form an ocean covering 90% of the planet. Yet Venus Express detects only a small amount of water vapor in the atmosphere. If you condensed all that vapor onto the whole planet, it would create a layer of water barely an inch deep. If Venus once had a vast ocean, what happened to it? Most scientists once thought it simply boiled away. But as Venus Express orbits the planet, scientists are forming a new theory. They believe the culprit is still the sun, but the cause is more than simple evaporation. The sun sustains life on Earth. It also blasts out a constant stream of deadly charged particles. They race out at speeds of up to 1,800,000 miles an hour. It's called the solar wind, and it can devastate unprotected planets. Surrounding Earth is a magnetic field that safeguards our atmosphere. This field is formed by movement in our iron core as the planet spins. But Venus has no magnetic field. Scientists believe it may rotate too slowly to generate one. The rotation is so slow, a day here lasts almost 2/3 of an Earth year. On Earth, one rotation takes 24 hours. On Venus, 243 days.
Well, without a magnetic field like Earth's, Venus is much more vulnerable to being affected by the solar wind and by energy in the upper atmosphere, stripping the atmosphere off into space.
Scientists now believe a combination of evaporation and solar wind stripped the planet of its moisture. Venus is closer to the sun than we are, therefore hotter. Its primeval seas evaporated into the atmosphere. That water vapor might still be trapped in the clouds, if not for the solar wind.
The oceans ultimately boil off, and then when you have all that water as vapor in the atmosphere, it's very vulnerable to being broken up by ultraviolet sunlight into hydrogen and oxygen, and then the hydrogen escapes into space, and there you have it. After a few billion years, you've lost your oceans.
The solar wind smashes into the atmosphere, ripping the molecules from the clouds. Over billions of years, the water is lost in space. The oxygen and hydrogen detected in the atmosphere are the last drops of those ancient oceans. Loss of water turned Venus from a warm, wet planet to a burning rock. The atmosphere changed too, from water vapor to carbon dioxide. Ancient volcanoes released trillions of tons of CO2 and set off a chain reaction, a runaway greenhouse effect, leading to global warming gone mad.
The energy for both climate and weather on planets all comes from sunlight. So now imagine that this is sunlight heading towards the surface of a planet. And on a planet like Earth, where there's not much atmosphere, as represented by these atmospheric molecules here in blue, most of the sunlight will miss the atmosphere and just make it to the surface. And occasionally you'll have sunlight scattering off an atmospheric molecule. But for the most part, you just have these yellow rays of sunlight reflecting off the surface. Now, let's set up again and look at what happens on Venus. And I'm putting much more gas in the atmosphere because now we're simulating Venus, which has 100 times as thick an atmosphere as Earth. Okay, so here's our thick Venusian atmosphere. Here we are back out in space, and let's see what happens to the sunlight in this much thicker atmosphere on Venus. And you'll see maybe a very occasional ray of sunlight hits the surface, but in almost all cases, it gets absorbed in the atmosphere.
The trapped sunlight heats up Venus's atmosphere, and any sunlight that reaches the surface worsens the situation.
So here we are on Venus, our hot surface radiating infrared. And is it making it out into space? Generally, no. Not only is it getting absorbed into the atmosphere, but some of it is bouncing back to the surface. And so on Venus, the infrared radiation is trapped by the thick atmosphere, and the surface and the atmosphere end up heating up.
The process resembles what's happening on Earth, but on Venus, it's out of control. Earth's twin is now the hottest planet in our solar system, even hotter than Mercury, the planet closest to the Sun. Venus is the poster child for climate catastrophe, devastating global warming, and a cosmic hellhole. If Earth were nearer to the Sun, it would look like Venus.
The major difference between Earth and Venus in terms of the evolution of the planets is all about Venus being closer to the Sun. We think that they formed kind of as identical twins, and then it's a different sort of experience of growing up in slightly different neighborhoods closer to the Sun and farther from the Sun that led to this huge divergence we see today.
Life on Earth may be a lucky break, but in the end, we share the same fate.
If you think of the long-term future of the Earth, Earth will go the direction of Venus because the sun is heating up. And I'm not talking about on a short time scale. If we think about billions of years in the future, really, cosmological timescales, then Earth is destined to end up like Venus.
Scientists long guessed Venus was once like Earth. Venus Express has shown how it evolved into a barren world. More revelations lie beneath the clouds. On the surface, the clouds look calm. But when the spacecraft switches on its infrared thermal imaging spectrometer, its images show how the scene transforms. Violent storms rip across the planet. At the poles, monster cyclones churn the atmosphere. Storm systems that make Earth's worst weather look like a breeze. As scientists study this mysterious planet, they make a startling observation. While Venus rotates slowly, its atmospheric winds travel fast. Venus Express observes winds circling the planet in a mere 4 Earth days. That's 60 times faster than the planet's rotation speed. Scientists call this superrotation. If Earth were like Venus, winds would whip around the planet in just 30 minutes. A speed of 50,000 miles per hour.
When you think about the rotation of the Earth, you've got the rotation rate of the solid planet, 24 hours, and then the atmosphere sort of going along for the ride. But with Venus, it's almost as if the atmosphere doesn't really care what the solid surface is doing. It's got a mind of its own, and is rotating much faster than the solid surface.
On Earth, wind speed nearly matches rotation speed. So why do Venus's winds travel so much faster than the planet spins? The answer lies in the clouds. On Venus, the cloud layer is up to 12 miles thick. So thick, only a small amount of solar energy reaches the surface. Much of this energy is retained in the upper clouds, 40 miles above the surface. This energy starts the clouds moving at breakneck speeds. Because Venus is closer to the Sun than Earth, the greater the solar energy in its clouds, and the greater the wind speeds. Winds rare on Earth, over 200 miles an hour, are typical on Venus. Venus Express is equipped to solve a riddle found by an earlier mission. A vortex at Venus's North Pole, similar to vortices on Earth. We call them hurricanes. On Earth, they form when warm, moist air from the ocean is heated by the sun and rises to form clouds. As more energy enters the system, the clouds start to spin, creating a hurricane. But Venus has no warm oceans for fuel. So what powers its hurricanes? Venus Express swings down to the southern hemisphere for a closer look. What it finds blows scientists away. A vast hurricane-like vortex, 1,200 miles wide and 13 miles deep, 4 times larger than the largest hurricane on Earth. Not one, but 2 rotating eyes. Scientists believe the cause of the vortices is not only super fast winds, it's the very motion of the planet.
A huge vortex is caused by all the air flowing in from the equator, and then it has to sink somewhere, which causes this enormous vortex, which is some 2,000 kilometers across.
Wilson believes air from the equator flows to the poles, where it's sucked down to form the vortex. But this air doesn't move in a straight line. The planet's rotation deflects its motion. He suggests this process, called the Coriolis effect, produces the giant vortices.
Let's explain the Coriolis effect using this rotating table. It's the same for a rotating planet. If I let this ball roll across the table, you'll see that it runs in a straight line. And that's because you, the observer, are stationary. You're not rotating with the table. Whereas if, on the other hand, we switch to a camera angle or another observer who's rotating with the planet, this ball will appear to travel in a curved trajectory. So if the observer is rotating with the planet, then it appears that objects experience a force to the right. And this works not only for balls, but also for parcels of air in the atmosphere. If the air at Venus is heated at the equator and moves towards the poles, it's then bent towards the right if it's in the southern hemisphere, or towards the left if it's in the northern hemisphere.
As the winds move toward the poles, the Coriolis effect makes them spin, which creates the vortex. Wilson's theory seems logical. Vortices also occur at Earth's poles. But while Earth's polar vortex is relatively stable, the double-eyed monster on Venus is an ever-shifting whirlwind. To find out what makes the vortex so chaotic, recreate it. Wilson uses water to simulate Venus's atmosphere.
We've got the rotating atmosphere simulated by the rotating tank, and then we've got this thin ring here which spins at a different speed, faster than the rest of the atmosphere. And what we find is that the flow in this region is unstable. It sort of oscillates in and out. And we think that's quite representative of what happens around the edges of the polar vortex on Venus.
When Wilson adds dye, his simulation reveals the shifting shapes at the edge of the vortex. These chaotic winds show the power of Venus's atmosphere. But vortices aren't the only bizarre weather. On June 9th, 2006, Venus Express discovers an eerie phenomenon. The spacecraft detects an intermittent disturbance that sounds like a whistle. A brief, low-frequency electromagnetic burst. This is the actual recording. To anyone else, baffling. But to the mission team, a revelation. The signature of lightning. UCLA's Professor Christopher Russell has long believed lightning occurs on Venus. The spacecraft's discovery presents a riddle. On Earth, water drives thunderstorms. Warm, moist air collides with cold air. Water droplets and ice crystals rub together, creating positive and negative charges. The electrical buildup discharges as lightning. Venus's atmosphere has little water. Most of it has been stripped away by the solar wind. So what else could produce lightning? Thanks to data from Venus Express, a controversial theory gathers new weight. Russell's candidate for the cause of lightning? Clouds of sulfuric acid. On Earth, sulfuric acid clouds form when sulfur dioxide is released from volcanoes and mixes with water vapor. The same thing happens on Venus. 2 decades ago, Project Magellan, the first spacecraft to map Venus, discovered widespread evidence of a volcanic past. Over eons, volcanoes release trillions of tons of sulfur dioxide. Some remained as a gas. The rest mixed with water vapor to form sulfuric acid clouds. The speeding winds energize these acid clouds and create ideal conditions for lightning.
We think now that it's sulfuric acid clouds and Venus's winds, and the winds can then provide the energy source in the cloud for the charge separation.
Sulfuric acid does on Venus what water does on Earth. Acid drops rub together and create positive and negative charges.
I was looking for lightning and looking for the proof that it really existed, and to find it is like a personal victory.
The discovery of lightning is electrifying. Lightning is an ingredient of life. An even greater shock was in store. The hellish planet might not be dead. Eons ago, Venus's volcanoes spewed out vast clouds of sulfur. But today, tests show the level of sulfur is fluctuating. Since volcanoes discharge lots of sulfur only when they erupt, the fluctuations mean one thing. The volcanoes on Venus must still be active. Scientists have found active volcanoes in only a few places besides Earth. In 2007, the New Horizons probe captured an eruption on Io, one of Jupiter's moons. To find active volcanoes in the inner solar system is big news. It means Venus may not be a dead rock, but a living planet. Venus Express takes a closer look. The probe exploits the infrared windows to peer through the clouds. Below, mountains and valleys, smooth plains, impact craters, and flat-top features like pancakes, all made of lava. 85% of Venus's surface is paved with lava. Why so much? Puzzled scientists. To understand Venus's vast lava fields, scientists look to its calmer twin. Earth's crust is made up of interlocking tectonic plates that drift over its liquid mantle. Most of our planet's volcanic activity is found where these plates move together or pull apart, allowing heat from the core to escape. No mission has ever found evidence of plate tectonics on Venus. Its crust is solid. Without plate tectonics to cool Venus, scientists suggest heat from the core built till it couldn't be contained. Then virtually the whole planet erupted, releasing so much lava, it recycled the crust and resurfaced the planet.
This is a demonstration of the Venus resurfacing. We're going to demonstrate with some pudding in a pan over a hot plate. And this heat from the hot plate represents radioactive heat from the inside of Venus. And here we're seeing the first signs of the interior heating the crust on the surface. And that crust is stagnant. It's not moving, it's keeping the heat inside. And perhaps at this moment, the surface might even crack in some places, and the molten material, the molten rock under the crust, would erupt and flow out onto the surface, covering up all the craters and all the mountains. And at this point, we can see several small volcanic eruptions along those fissures.
Scientists date the resurfacing to 500 million years ago. A slow process that took tens of millions of years. This cataclysmic series of eruptions released trillions of tons of sulfur dioxide and carbon dioxide, replenishing what the solar wind removed. Yet surveys of Venus reveal not all the planet was resurfaced. Rocks in the highlands are much older than the lava covering most of the planet. They offer a clue to conditions in the distant past. Kevin Baines discovered these rocks weren't born on dry land.
On Venus, most of the rocks are basalts. They're made out of volcanoes spewing out their lava. But we have found a very interesting result in the last few months. That is, the highlands are special. On the highlands, the tall mountains of Venus, we're finding evidence of rocks that were created in the presence of water, as if billions of years ago they were formed perhaps in an ocean, and then geologic processes have risen them up since then.
The rocks provide hard proof that Venus once had oceans, which raises a provocative question. On Earth, life began in the oceans. The other ingredient to kickstart life is lightning. And lightning occurs on Venus. If Venus had water and lightning, did it once have life? Scientists have plenty of proof that Venus and Earth were once twins, and that Venus had two of the ingredients of life: water and lightning.
Lightning is important because it's something that produces exotic species. For example, nitrogen and oxygen combine to produce nitrogen oxides, which are important for life and important for producing chemicals that can't be produced any other way in a planetary environment.
With water and the means to kickstart evolution, perhaps Venus once had life, and maybe still does. The first clues arrive from Venus Express. 155 miles above the surface, a camera is switched to ultraviolet. Unlike infrared, the shorter wavelength of UV is scattered by Venus's cloud layer, enabling the scientists to explore the upper regions of the atmosphere. Their images reveal intriguing dark markings where more UV is being absorbed. This shows that something besides sulfuric acid is trapping sunlight. The mission team calls the dark areas absorption patches.
There's been great interest in the ultraviolet absorbers on Venus. They absorb about half of the sunlight that's hitting the planet. They're in the clouds of Venus, and it's been suggested that they might be associated with life forms.
Life forms, like microbes, living in hurricane-force winds and sulfuric acid clouds, using UV light in some weird photosynthesis. But what kind of life could survive such conditions? Biologist Lynn Rothschild studies organisms that live in extreme environments. She has discovered microbes called extremophiles thriving in some of the harshest conditions on Earth. Like Yellowstone National Park, the highest concentration of thermal springs in the world, it opens a window into how life might survive on Venus.
What you see behind me is really ground zero for where people started to understand organisms that could live in extremely acidic conditions. Before that, people thought conditions like lemon juice would be totally outside the realm of where a living organism could be.
These geysers, powered by volcanoes, mimic conditions on Venus, hot and acidic.
This stream is just phenomenal. It's about pH 3, it's about 40 degrees centigrade. A little hotter than warm to the touch. Actually, it's fairly warm to the touch. And what you see in here is almost a pure culture of some red algae. I know it looks green, but they are actually red algae that don't have a red pigment.
Extremophiles like these can survive in battery acid and temperatures above boiling point. These organisms have evolved to survive not only the heat and the acid, but levels of other chemicals that would kill most life.
These particular organisms, Cyanidium, are really neat because not only do they live at low pH and in warm temperatures, and they photosynthesize, but they've been shown to be able to survive in pure CO2, pure carbon dioxide. Even Venus doesn't have as high a carbon dioxide level as that.
The organisms show life can survive hot, acidic carbon dioxide-rich environments, like Venus. If life can survive in Yellowstone, why not on Venus? Scientists believe the surface itself is too savage. Temperatures reach 900 degrees, and the pressure is bone-crushing. But not in the clouds. 30 miles up, temperatures reach only 176 degrees, much closer to the kind of heat microbes endure on Earth. Could life have begun in Venus's ancient oceans? When the water evaporated, the microbes may have gone with it. Here, in the cooler acidic clouds, they could survive. But how can life exist without water?
There is water vapor up in the clouds in Venus, and we have some indication that organisms on the Earth, for example, lichens, can use water vapor as their source of water. So that's pretty encouraging for life in the clouds, at least in terms of having water available.
To see if life exists in moist, acidic clouds, Rothschild collects air samples above a hot spring. The acidic steam mimics the clouds of Venus.
I can see a little green on the mouth here. That's encouraging. Maybe there really is something in there.
Analysis shows microbes can exist in hot, acidic steam, suggesting life may survive in Venus's clouds. To further test the theory, Lynn sends organisms high into the atmosphere. She's launched a whole spectrum of microbes. Some to over 100,000 feet. A zone where temperature and pressure drop so low, most life would die.
Okay. Now let's hope we put enough in it.
Many of her subjects survived. Some researchers have even found organisms that can reproduce high up in the atmosphere.
The clouds on Venus are continuous and long-lived. So you can imagine creatures that live in the clouds and reproduce in the clouds and even seed other cloud particles. And they're not going to last forever because they're going to fall out, but as long as they last long enough to reproduce themselves, then you could have a self-sustaining colony of life in the clouds.
Research shows life in hot, acidic clouds is theoretically possible. Perhaps microbes live in the clouds of Venus, hidden in those strange dark patches. Venus Express has traveled 87 million miles around the planet and completed 100 weeks of collecting data. It proved that Venus once looked like Earth. A habitable climate, vast oceans, perhaps even life. But too near the sun, Venus was doomed. Earth blossomed, Venus burned. Yet even here, life may thrive. Maybe tucked in blankets of clouds. We may have to wait years for the secret to be revealed. But someday, another mission to Venus may find the holy grail of space. Life beyond our world. Stephen Hawking is the world's most famous scientist. He's on a quest to answer the biggest question of all. How did everything in the universe come to exist?
If we find the answer to that, we would know the mind of God.
Hawking's goal is to discover a blueprint for the universe. But he's locked in a battle with a disease that has left him paralyzed. And it's advancing. Can he unlock the secret of creation before his time runs out? Stephen Hawking is one of the greatest thinkers of all time. He's on a quest to understand the moment of creation, when the universe is born. 20 years ago, he writes a book on the subject that becomes an international bestseller. It promises that soon he will have a single theory so powerful, it will explain all the mysteries in the cosmos. Why did the universe spring into life? And will it ever come to an end? A theory of everything.
We are getting close to answering the age-old questions. Why are we here? Where did we come from?
His determination to find answers has kept him alive far longer than any doctor predicted.
Stephen has got tremendous determination to solve the problems of the universe. And I think that's one of the key factors which has kept him going all these years.
But he lives his life on borrowed time.
The idea that my father had a very short lifespan was always present. I think it was there every single day.
Hawking will not rest until he unlocks the secret of how the universe came to be.
My goal is simple. It is a complete understanding of the universe, why it is as it is, and why it exists at all.
Born in 1942, Stephen Hawking has always been fascinated by the world around him. As a healthy child, he wonders what made the stars. By the time he's a teenager, he wants to find out where the entire universe came from. In the 1960s, scientists have yet to answer that question. Many believe our universe had no beginning. It is timeless and unchanging. But a new theory gains ground. Everything in our universe exploded from one tiny point, like a shower of fireworks. Scientists nickname it the Big Bang. But how can we suddenly go from nothing to everything in one moment of creation? Just 20 years old, Stephen Hawking's first mission is to find out. In 1962, he's just started his PhD at Cambridge University, where he's eager to prove himself. According to his old friend Kip Thorne,
Stephen was beginning to develop a reputation at that stage, but just barely beginning. It was not at all obvious at that point that he was going to come to tower over all the rest of us.
but it's around this time that Hawking notices he's becoming very clumsy. A visit to the hospital leads to a startling diagnosis. Doctors discover he has amyotrophic lateral sclerosis, or ALS. The disease wastes his muscles. Before long, he will be completely paralyzed. Within 2 years, he will be dead. Hawking is just 21. His dream of unraveling the mysteries of the universe crashes down around him.
I had just been diagnosed with ALS, and I didn't know if I would live long enough to finish my doctorate.
It's the darkest period of his life. According to his daughter, Lucy Hawking,
he became very depressed and very saddened. He was casting around at the time for a PhD topic, but he didn't really see any point in going on, so I think everything seemed very bleak and very hopeless to him.
But then Hawking meets Lucy's mother, and they fall in love, despite his death sentence.
Getting engaged and getting married to her was for him the turning point, that was the event for him that turned him around and gave him hope and made him decide that he was going to carry on.
Hawking sets out to discover the origin of the universe before his time runs out.
Does the universe, in fact, have a beginning or an end? And if so, what are they like?
Scientists remain skeptical that something can come from nothing, as the Big Bang predicts. Hawking wants to find out. His first break comes in 1965. He attends a lecture by a brilliant mathematician named Roger Penrose. Hawking hears something that grabs his interest.
Stephen was in the audience at the back of the room, and he was asking some very pertinent and difficult questions.
Penrose suggests something astonishing. There's a hole in space where huge objects disappear. If matter disappears into nothing, maybe it can also appear from nothing. This could be Hawking's first step towards proving the Big Bang. But how can there be a hole in space? The answer might lie with gravity. Einstein's general theory of relativity says gravity isn't just a force of attraction, it actually bends space. Oxford University physicist Pedro Ferreira studies gravity's impact on the universe.
Well, Einstein realized that gravity wasn't this force that acted between two bodies. It was something much more elegant and beautiful.
Einstein pictures space and time as a fabric. Planets and stars press on this fabric and create dips. In a stroke of genius, he realizes gravity is not a force, but the bends in this fabric. The dips pull objects towards them.
Let's imagine this rubber sheet is space. These glass balls that I'm holding in my hand are planets and stars. Now, if you place a planet or a star in the universe, on space, it'll create a dip. And the bigger the object you place, the bigger the dip. Imagine that the Earth is this coin, and I just send it coasting round our sun. It'll settle nicely into an orbit. It's just following the deformed nature of the fabric of space. That's what gravity is, and that's what Einstein realized.
So what we experience as gravity is actually the curve of space-time around us.
The theory of relativity does force us to fundamentally change our ideas of space and time.
When that fabric gets stretched to breaking point, something dramatic happens. A hole in space opens up. A hole down which things can disappear. This chain of events starts when a star dies. It begins to collapse in on itself, getting smaller and denser. If a star 20 times the size of the Sun dies, it has a drastic effect on the fabric of space-time.
If you imagine what this means in terms of the fabric of space-time, you're just pressing down on it incredibly hard. You're pressing so hard on it that at that point, it almost tears.
The depression is so deep that nothing can climb out, not even light. This is known as a black hole.
If this star is big enough, it'll collapse to a tiny, minute point, incredibly dense. And it'll create a dip in space, so deep that if an object tries to pass by, it'll be sucked in, it'll be sucked all the way down into that point. That's a black hole.
Roger Penrose discovers that at the center of a black hole is a point of pure gravity. It's called a singularity.
As you go into a black hole, you will encounter something which goes against the laws of physics as we previously understood it. Roughly speaking, you could say a singularity is where space and time come to an end.
A singularity is like a drain, a hole in space. Everything that falls down it disappears. Hawking wonders if the opposite could be true. According to the Big Bang Theory, all the universe suddenly sprang from a point of nothing. Could this hole be the key to explain how this happened? In a moment of genius, he sees the solution. It's elegantly simple.
I soon realized that if one reversed the direction of time in Penrose's theorem, the collapse became an expansion.
Instead of sucking everything in, a reverse black hole explodes out in a shower of space, matter, and time. Exactly as the Big Bang Theory predicts. Against a sea of skepticism, Hawking proves the universe suddenly appeared from nothing. It sprang from inside a singularity. The debate is over.
The universe must have had a beginning in time. This was finally proved by Penrose and myself, on the basis of Einstein's theory of relativity.
Hawking found the origin of time, but he hasn't found a way to stop it ticking. He's now 26 years old. His disease has advanced up the muscles in his legs. He can no longer walk. But his brain is alive with questions. Hawking now knows a moment of creation happened, but not what caused it to explode into being. This will prove his biggest challenge yet. Can he find the answer before his body collapses? Stephen Hawking has discovered where the universe began. A tiny hole in space, known as a singularity. This exploded in a big bang to create everything in the universe. But he doesn't understand what made it explode.
Why are we here? Where did we come from?
To find the origin of the universe, Hawking used Einstein's general theory of relativity. Relativity explains how gravity acts on large objects like stars and planets. But when the universe was born, it was smaller than an atom. So to understand how it grew, he needs the theory of the very small, quantum mechanics. The trouble is atoms are unpredictable. They don't follow the ordered rules of gravity. The theories of general relativity and quantum mechanics are incompatible.
Unfortunately, these two theories are known to be inconsistent with each other. They cannot both be correct.
At NASA Goddard Space Flight Center, Kim Weaver is interested in the conflict between the theories.
In a way, this ball can be used to represent the tension, or the battle actually, that's going on between general relativity and quantum mechanics, quantum physics. The surface is smooth. It represents a large scale. General relativity, gravity, acts on a very large scale. And we can predict what's going to happen based on those equations. But if we zoom into the quantum world, things are very chaotic, and these larger scale laws don't apply.
We used to think that electrons orbited around the nucleus of an atom, like planets around the sun. But scientists now know that electrons pop up and disappear at random. They can even be in more than one place at the same time. Normally, gravity appears to play no part in this chaotic world. But at the moment of the Big Bang, there was a huge amount of matter held together in a tiny space. So gravity must have had a role.
Bringing these two ideas of general relativity and quantum mechanics together into a unified whole is what Stephen Hawking set out to do.
He wants to combine the two theories into a theory of everything in order to find out what triggered the moment of creation.
If we find the answer to that, it would be the ultimate triumph of human reason.
Hawking knows the theories of gravity and quantum mechanics clash at the instant of the Big Bang. But he believes they also clash inside a black hole. This is where a huge amount of matter crushes to a tiny point. So he returns to black holes to investigate. If he can unite the two theories here, it could help him understand the Big Bang. Relativity says nothing can exist on the edge of a black hole. Everything is sucked in. But quantum mechanics states that space is never empty. It's full of tiny pairs of particles.
Space is essentially empty to us, and it is empty when we look at it. It appears to be empty. But at this very tiny level, it's not at all. In fact, it's filled with virtual particles coming into existence and annihilating each other all the time.
Energy waves in space create tiny particles. Every particle has an antiparticle. One has positive energy, and the other has negative energy. These pairs appear, but then collide and destroy each other.
Quantum mechanics was very well established, but no one knew how it played into the larger scale of the universe. And that's where Stephen took those two things and said, let me now play with this in my mind. How does this work? If I put a virtual pair next to a black hole, what happens?
To unlock the secrets of a black hole, Hawking must discover what happens to these particles. Now 28, his body is wasting away, but his mind doesn't let him down. He has a flash of inspiration. The answer lies with the fact that the particles are positive and negative.
And what Hawking realized, what's really fascinating about this, is when a pair of particles like this appears near the event horizon of a black hole, the one with negative energy falls into the black hole, and the one with positive energy escapes as radiation.
The negative particle is pulled into the black hole, but the positive particle has just enough energy to avoid getting sucked in. It's released as a particle of radiation. Hawking has proved black holes give off heat, and these positive energy particles are the source. It's called Hawking radiation. The revelation that something can escape the grip of a black hole shocks the world.
When I first announced the results of my calculations, I was greeted with incredulity. By their definition, black holes are not supposed to emit anything.
Hawking proves that while gravity sucks in the negative particle, quantum mechanics allows the positive particle to escape. The two theories can work together. It's the closest anyone's ever come to a theory of everything. But while the world celebrates Hawking's discovery, privately he is concerned. His theory of everything has a fatal flaw. Stephen Hawking is on a quest to unite the two opposing sides of modern science: general relativity and quantum mechanics. If he achieves it, he will have a theory of everything. One equation that could reveal the underlying plan of the universe. It might even explain how it exploded into being. To find it, Hawking needs to piece back together an explosion that detonated 14 billion years ago, the Big Bang. But how? His starting point is an astonishing prediction. Black holes explode, and in a way that makes them very similar to the Big Bang. Hawking discovered that unlike negative particles, positive particles can escape the gravity of a black hole. Now he takes his theory a step further and discovers that over time, a black hole begins to evaporate like a puddle in the hot sun. Over billions of years, it sizzles away. As it gets smaller, it gives off more radiation. It shrinks faster and faster until it shrivels right out of existence. And at that moment, something dramatic happens.
The most reasonable guess is that it would disappear completely in a tremendous final burst of emission, equivalent to the explosion of millions of H-bombs.
It's this tremendous explosion from a tiny point that grabs Hawking's interest.
The Big Bang resembles a black hole explosion, but on a vastly larger scale.
So Hawking's question is, could anything come out of the black hole when it explodes? If it is similar to the Big Bang, will it release a high-energy stew of particles, like in the early universe?
An understanding of how black holes create particles will lead to a similar understanding of how the Big Bang created everything in the universe.
It could be a mini version of the moment of creation. But all of this is theoretical. No one knows if black holes do explode. Now, for the first time, we may actually see this happening. On June 11th, 2008, NASA launches a state-of-the-art telescope called Fermi. The telescope will search the vast expanse of space for the last gasp of a tiny black hole. As it dies, it should release a huge blast of high-energy particles called gamma rays. That's what Fermi should see. Steve Ritz is the lead scientist.
What we'd be searching for is a tiny object, a microscopic object, no bigger than an individual proton, the core of a nucleus, and yet it's shining apparently like one of the brightest objects in the whole sky.
But Fermi's search for these black holes isn't easy. There's a flood of gamma rays from exploding stars that could mask an exploding black hole.
So here's what the whole sky would look like if you had gamma ray eyes. We'd hope to see the individual black hole at the very end of its lifetime making an explosion. And that could happen really anywhere on this image. And that's why it's so incredibly interesting, because one of those contributions could be the individual primordial black holes producing their Hawking radiation.
Ritz's team continues to search for a black hole explosion caused by Hawking radiation. These events are rare, but the payoff is huge, so the search continues.
It would be incredibly exciting if we discovered a family of gamma ray bursts that had no other explanation than the Hawking radiation from microscopic black holes. It would be a revolution in science.
While Fermi searches for clues to how the universe kick-started into life, Hawking's uncovered a mystery that could derail his quest for a theory of everything. In the moment after the Big Bang, something strange happens to gravity. For some reason, it suddenly changes gear and gets weaker. And this is crucial to our existence today. If gravity hadn't weakened, it would have yanked all matter back in on itself. And the universe we know today wouldn't exist. The mystery is, why did gravity weaken just enough to stop the universe from recollapsing? Hawking needs to find a way to explain this.
If we want to know what happened when the universe began, we have to have a theory to explain gravity on a very small scale.
Gravity is actually the least understood force in nature. It's much weaker than the other forces. Consider electromagnetism, for instance. Electromagnetism is the force that tears up our skies in violent storms. It also binds atoms together into everything we see around us. At the instant of the Big Bang, scientists think electromagnetism and gravity are the same strength. As the universe expands, gravity dramatically weakens. Sean Carroll is a cosmologist who studies gravity at the moment of the Big Bang.
Gravity is something we notice every day. We drop things. We have to work against it to climb a set of stairs or to move around. It seems to us like a powerful, important force in our lives. So the puzzle is that, in fact, gravity isn't really as strong as we think. I can take something very, very tiny, like a set of keys, and if I drop it, it could smash something far below. Nevertheless, something as small as this magnet can be more powerful than gravity just because the electrical and magnetic forces here are intrinsically more powerful. Just a tiny little magnet is able to overcome the gravitational force exerted by the entire Earth.
Nobody knows why, after the Big Bang, gravity changed gear and became weaker. Hawking's theory of everything should reveal the inner workings of the universe, but it can't explain this. Something is wrong with the blueprint. He sets to work trying to puzzle it out. He now has the top minds in the field working with him. but only a few members of this inner circle can understand his speech. He must painstakingly dictate his scientific papers. The process is slow, but he is making progress. His family worry he is pushing himself too hard.
There was always this terrible, terrible fear whenever anything went wrong, or when he started choking or coughing, or he got an infection, that this was it. Because you just never knew what might happen next.
Then in 1985, on a trip to Geneva, Switzerland, tragedy strikes. Age 44, Hawking collapses with pneumonia. An emergency tracheotomy saves his life, but severs his vocal cords. Unable to communicate, completely cut off from the world, Hawking plunges into his own black hole. 6,000 miles away in Lancaster, California, speech software designer Walt Woltosz gets an urgent call from a friend about a new client.
He mentioned that he was a physics professor at Cambridge. I said, gee, that sounds like Stephen Hawking, you know, and he said, well, I'm not allowed to say. And I said, well, I'll tell you what, if it is, I'll donate whatever he needs.
Hawking is able to make a slight movement with his fingers, so he can use a switch. Woltosz designs an ingenious system that helps predict the words Hawking will use.
I choose the letter B, and I'm going to choose the word black here. Now, after I selected the word black, and in Stephen's case, the word black is almost always going to be followed by the word hole. Now, if I want to speak that, I can just choose the speak command here.
Black hole radiation. Woltosz sends the machine to Hawking, and the voice we hear today is born.
I like my present voice, even though it has an American accent.
It's the breakthrough Hawking needs to carry on with his work.
The first time I came back to see him after the initial time, he was scanning at 10 steps per second. This is blinding speed.
He'd sort of risen like the phoenix from the ashes to be this new character with an American electronic voice. And he's so sort of good-humoured about it that you just felt admiration, I suppose.
Never in these circumstances have I ever seen him show frustration. He just keeps going at it.
Hawking returns to Cambridge and click by click presses on with his work. He employs a team of graduate students to help with the computations.
I'm going to talk about...
He's been given another shot at cracking the theory of everything, and he's more determined than ever. Stephen Hawking has spent 3 decades trying to discover a theory of everything, a powerful set of laws that governs the entire universe, from the tiniest particle to the largest galaxy. It's been the holy grail of theoretical physics for over a century. Hawking painstakingly lays the groundwork for this theory, but he could be beaten to the finish line by a radical new theory, string theory. One of its architects is physicist Michael Green.
It represents such a profound change in our way of thinking of the universe, both in the very small and in the very large, that it should have all sorts of repercussions.
String theory could even be a candidate for the theory of everything. It unifies every single thing in the universe, from atoms to stars, planets to people, because they are all made from one ingredient, strings. Strings are so tiny, there's no way to see them directly. Equations show they could be a trillionth the size of an atom. To get an idea of how small this is, imagine an atom blown up to the size of our solar system. The nucleus would be the size of our sun. But even in this scaled-up world, strings are tiny, smaller than the Earth, smaller than the smallest state, about as tiny as one person in our entire solar system.
I would be the size of a string.
Strings are the building blocks of everything we see around us. The entire universe is a gigantic mesh of these vibrating strings.
We're all made of string, and we're moving in a stringy space-time, and everything is stringy.
To correctly describe our universe with string theory requires something incredible. The world we see around us is made up of 3 spatial dimensions: width, height, and length. But Green and his colleagues think that we are actually surrounded by at least 9 dimensions. This may sound like science fiction, but Green suspects these extra dimensions are hidden from our view.
Clearly, since we don't see these extra dimensions in everyday life, they must, in some sense, be very small and not directly observable.
Green collaborated on his theory with Caltech physicist John Schwartz.
We have the perception that we live in this 3-dimensional world, even though it may in fact be more dimensions.
But how can there be dimensions that we haven't noticed?
This is a line, which is a 1-dimensional object. But if we turn it around and look inside, we can see that it's actually a rolled up piece of paper, which is a 3-dimensional world. We can see that there's an inside, and if we put an ant in here, the ant can go around in 3 directions. So the ant sees it as a 3-dimensional world.
The extra dimensions reveal themselves if, like this ant, you're small enough to see them. Schwartz believes these extra dimensions are curled in on themselves, curled up into tiny knots that are so small we can't see them.
But the fact that we don't see them doesn't mean that they don't have a profound effect on the universe we live in.
Schwartz and Green believe these extra dimensions explain why gravity is so weak. They believe at the moment of the Big Bang, gravity is strong, but then the universe expands. Gravity spreads out into the extra dimensions, weakening as it goes. This explanation removes the final stumbling block to the theory of everything.
Let's consider an analogy in which gravity is like music. When I'm close, it's loud, and as I walk away, it gets quieter.
The music disperses in different directions. As it does so, it weakens.
Here, the music is almost inaudible, and that's because it's spread out over space. Now imagine, instead of music, that we're talking about gravity, and imagine that there are extra dimensions in space. Extra dimensions in which the gravity can spread out even more.
More dimensions in space mean more directions to spread across. This in turn makes gravity even weaker. String theory explains how the universe we see today exists. After the Big Bang, as the universe expands, gravity spreads out through these tiny extra dimensions and weakens. Gravity weakening is what stops the universe from collapsing back in on itself. It's the missing piece in Stephen Hawking's quest for the theory of everything. He concedes that Green's string theory is the best contender to explain how the universe came to be.
Stephen Hawking's relation to string theory is very intriguing. I think he's a big admirer, but not necessarily a believer. His ideas have had a profound influence, actually, on many things that have happened in string theory. And with a bit of luck, string theory has had some influence on his ideas as well.
We believe that there is one fundamental theory that describes dimensions that are curled up so small that we don't notice them. Nevertheless, These hidden dimensions affect physical quantities like gravity.
One hitch is that none of this has ever been proved. String theory and the extra dimensions exist only on paper. Like so many of Hawking's own discoveries, there is no proof. But that might be about to change. And the earliest moments of the universe could soon be revealed. This is the CERN laboratory in Geneva, Switzerland, home of the Large Hadron Collider, the biggest experiment ever built. Deep below ground, scientists are attempting to recreate the conditions that existed just after the Big Bang, to reveal how everything around us came into being. Scientists will search for clues to what happens in a high-energy environment, like the one that followed the instant of creation. It's the moment Stephen Hawking has been waiting for.
Why is the universe the way it is? A new window on the very early universe will be opened.
Scientists will fire subatomic particles in opposite directions. The particles will travel for almost 17 miles, accelerating to close to the speed of light. Then they will slam into each other with a force trillions of times more powerful than dynamite. This high-energy collision will produce particles similar to those in the aftermath of the Big Bang. It should reveal the key ingredients of the universe, and possibly the recipe behind them. The Large Hadron Collider will take us as close as humanly possible to the moment of creation. And in an incredible one-two punch, it could prove that both string theory and Stephen Hawking are right. String theory predicts that we are surrounded by tiny extra dimensions. These extra dimensions trap gravity. If this is true, particles colliding in a small region could feel ultra-strong gravity. This could trigger matter to collapse on itself into a mini black hole, exactly as Hawking predicts. So rather than a Big Bang machine, the collider could become a black hole factory.
The black hole might actually grow because over time, the black hole will pull material into itself. It could grab onto molecules in the atmosphere. So its mass will increase. I have no idea what will really happen in that case, but that means that the experiment does need to be controlled well.
Researchers estimate it's theoretically possible. They could create mini black holes at the rate of 1 per second. Some people fear that just one black hole could swallow the Earth. It's a terrifying thought. Scientists at CERN, however, are putting their faith in Stephen Hawking. Hawking predicts that small black holes will evaporate. They should burn up almost instantly, lighting up like a Christmas tree.
They will produce little black holes, which will then radiate and decay and disappear, according to Stephen Hawking predicted many, many years ago. And that would be, of course, truly exciting.
If black holes do appear, it will reveal the secret of why gravity weakens after the Big Bang. Tiny extra dimensions in space.
If they found proof of extra dimensions, I would be completely staggered. It would be extraordinary, because we would have finally found that space had more than 3 dimensions, which is fundamental.
A fault in the complex machinery delays the big startup until spring 2009. Even then, it may take years to comb through the data for proof of extra dimensions and tiny black holes. After searching for a theory of everything for almost half a century, Hawking desperately wants to live to see the culmination of his life's work. So once again, he faces a battle against time.
There are grounds for cautious optimism that we may now be near the end of the search for the ultimate laws of nature, though much more work will be needed.
Stephen Hawking is nothing if not a fighter. He has taken on the biggest mysteries in the universe and cracked them. He found the birthplace of the universe. He forced the two opposing sides of modern science together to prove that it is possible to escape a black hole. An achievement he has mirrored in the battle with his disease.
The greatest thing I've learned from my dad is if you fall into a black hole, don't give up, you can get out of it again. And that's so clearly what he's done with his life.
Hawking has outlived his death sentence by over 40 years to become one of the longest surviving sufferers of amyotrophic lateral sclerosis in the world. But questions remain, and a single equation powerful enough to describe all of existence still eludes him.
Stephen's grit, his stubbornness, have contributed to his continuing vigorously ever so much longer than anybody ever expected. And I'm hopeful that he may still be around working on this 20 years from now.
Stephen Hawking is as determined as ever to find a definitive theory of everything for our universe.
Planet Earth, 4.5 billion years old. A solid ball of rock weighing 6 trillion tons. We are on a quest to destroy it. Using cutting-edge physics and planetary science, we will explore what could destroy our planet completely. A black hole?
It might seem harmless, but its gravity is strong enough to destroy the entire planet Earth.
A collision with the sun?
And before you know it, the Earth is falling into a fiery plummet.
A huge antimatter bomb?
Poof, okay, at a huge annihilation.
A giant rock from space?
You wouldn't want to be standing here 50,000 years ago.
Or perhaps a swarm of self-replicating robots.
It's been a nightmare of sci-fi.
These ideas may sound like science fiction, but they're all grounded in proven scientific fact. Our planet is seriously tough. It has survived everything a hostile universe could throw at it for 4.5 billion years. Yet in the past few decades, we have developed technologies so powerful that some people fear we could literally destroy the Earth. It's time to find out if they're right. 6 top scientists are about to reveal what it would really take to destroy an entire planet. Our first candidate is a black hole, the greatest destructive force in the universe. A black hole is what's left when a giant star collapses in on itself. The result? Gravity so strong that nothing can escape, not even light. Soon, we may be able to create black holes right here on Earth. Physicists use huge particle accelerators to try to recreate what happened after the Big Bang. But when they smash particles together, they also risk creating a black hole. Think of a black hole as Niagara Falls, and the water going over like space getting sucked in. This unfortunate kayaker has gotten too close. Just like a star getting too close to a black hole. Dr. Phil Plait, astronomer and author.
The water going over the lip of the waterfall is just like space itself falling into a black hole. If you're kayaking, no matter how fast you paddle, once you go over that lip, you're going down. That's the point of no return. And it's the same thing with a black hole. No matter how fast you try to get out, it's going to take you down.
The gravity in a black hole is fundamentally different from the gravity we experience in normal life. Normal gravity you can escape from, at least in theory. Cosmologist and golfer Professor Lawrence Krauss.
It's commonly said that what goes up must come down, but that's not always the case. For example, if I hit this golf ball here and I hit it well, it would go fairly far, but it would still come back down to Earth. If I hit it harder, it would go further and still come back down. But if I hit it with a speed of 5 miles per second, it would escape from the Earth's gravitational field.
But for the ball to escape from a black hole, it would have to move faster than the speed of light, and that is simply not possible. What goes into a black hole, planets, or even stars, never comes out. Our small planet wouldn't stand a chance. For anyone looking for a way to destroy the Earth, black holes are a good place to start. The trouble is, there are none close by enough to do the job. Unless we make one. That's where the atom smashers come in. With a lot of math and a gigantic machine, physicists can now generate atom-sized explosions that may be powerful enough to create microscopic black holes. They are trying to study the Big Bang. The force of the impacts recreates the particles that made up the universe in its earliest moments. Some of those particles may create microscopic black holes. That doesn't mean our planet is doomed. In theory, black holes this small would just evaporate like tiny soap bubbles. To destroy this, you need something bigger.
Black holes come in all sorts of different sizes. For example, at the center of our galaxy, there's a black hole of 1 million solar masses. If you took the mass of our sun and compressed it down to be a black hole, it would be the size of a large American city like Phoenix here. On the other hand, if you took something like this mountain here, which is maybe 1 million tons, and made it a black hole, it would be smaller than the size of a single atomic nucleus.
Somewhere along that scale, black holes get powerful enough to cause serious damage. To destroy the Earth, It turns out you need a black hole that weighs about the same as the Earth. The Earth is 8,000 miles across. But a black hole weighing that much would be the size of a marble. Professor Clifford Johnson, physicist.
Here I have a marble-sized black hole. It might seem harmless, but its gravity is strong enough to destroy the entire planet Earth. What would eventually happen is that it'll start sucking things in, slowly at first, and then it will grow in size. It will grow and grow and grow until it swallows the whole Earth.
To imagine what that marble would do to the Earth, picture what it does to a physicist.
The gravity is much stronger on one side of an object closer to the black hole than it is on the other side of an object, producing an effect that's called spaghettification, as that object is stretched out and pulled apart as it falls into the black hole.
A big enough black hole could do this to our whole planet. There's no way even the most powerful atom smasher could make a black hole this big. To destroy the Earth, we need to find one ready-made. Astronomers think there are 10 million or so black holes in our galaxy. If one of them strayed into our neighborhood, it could rip our planet to pieces. Earthbound telescopes may not even detect it. Humans would only know it was approaching when its immense gravity triggers huge floods and earthquakes. As it plunges into our atmosphere, the black hole acts like a vacuum cleaner, sucking with a force over 1,500 times Earth's gravity. Then it begins to distort the shape of the whole planet. Earth's surface stretches and tears apart. Finally, the hole hits and flies straight on in, heating and vaporizing matter as it goes. It starts to orbit the Earth, inside the planet itself, all the time devouring everything in its path. Gradually, the orbit slows. The black hole spirals down into the Earth's core. Eventually, it eats the entire planet. All that's left is the black hole itself. It's a devastating end for planet Earth. But fortunately for us, it's unlikely ever to happen.
If you want to destroy a planet, a black hole is a great way to do it. But the problem is, it depends on the kind of black hole. A microscopic black hole would just pass right through the Earth, and it really wouldn't do that much damage. A black hole with the mass of the Earth would be about the size of a marble, and that would do a considerable amount of damage passing through the Earth. But again, it might not destroy the planet. If you want to do the job right, you need a stellar mass black hole, something with about 3 times the mass of the Sun. That thing would come in and it would tear the Earth apart and gobble down the pieces, and it would be game over. The problem is, we don't know how to make any of these black holes. Technologically, we just can't do it. And with a naturally existing one, we don't know how to move them. So there's got to be a better way.
So if black holes don't work, time for a new approach. One surefire way to destroy the Earth is to change its distance from the Sun. Move the planet closer and it bakes. Move it out and we freeze, sending us into another ice age. Scientists have recently begun to realize that moving a whole planet might actually be possible. In fact, we use the same principle to slingshot space probes round the solar system. planet Earth could be just a few well-placed flybys away from a fiery death. What would it take to incinerate an entire planet? Answer: a nuclear furnace nearly 1 million miles across. It sounds crazy, but the truth is this will happen. It's just a matter of time.
As the sun gets older and older, it's going to actually get brighter and brighter. And within about 2 billion years, the Earth will be in an uninhabitable zone. It'll be like Venus. There'll be a runaway greenhouse effect. All the water on Earth will be destroyed, and the surface temperature will be about 1,000 degrees.
Eventually, the sun will swell and scorch the Earth, unless we somehow move the Earth away from the sun to save it.
Alternatively, if you were sufficiently evil, I suppose, you could imagine doing exactly the opposite. Harnessing sufficiently large objects to transfer gravitational energy to kick the Earth's orbit closer to the sun.
Easy to say, not so easy to do. The Earth weighs in at 6 trillion tons. Pushing something that big is quite a challenge. But there is a way. It's called gravity assist. Space probe engineers use gravity assists all the time. Take Saturn's Cassini-Huygens probe. It's the size of a school bus, one of the biggest probes ever built. To build up enough speed to fling the probe out to Saturn, it had to swing by Venus twice and Earth once. Each flyby stole energy from the planet and added it to the probe. The probe got a lot faster by altering the planet's course just a little.
The name of the game, we take a rock about 1 mile or 2 across and we move it so that it just passes the Earth the right way, and it'll steal energy away from the Earth. The asteroid will go flying off and the Earth will move in toward the sun. But we shouldn't just waste the asteroid when we can recycle it. If we're clever, we can take the asteroid and have it go toward the planet Jupiter. And then if we pass Jupiter in just the right way, it'll take that extra energy it stole from the Earth, give it to Jupiter, and then fall back toward the Earth. And if we aim everything just right, we get a conveyor belt of energy. We steal it from the Earth, give it to Jupiter, and then come right back. And in fact, we can use hundreds or even thousands of asteroids this way, continuously stealing Earth's energy and dumping it toward Jupiter. And before you know it, the Earth is falling into a fiery plummet.
First, you need to catch an asteroid. It's as big as a mountain, and it's traveling around 10 miles a second. Next, you need to attach rockets and boost the asteroid onto the perfect course. Next, repeat, thousands and thousands of times. Very slowly, over thousands of years, the Earth will fall towards the sun. Right now, we're just over 90 million miles away. By 70 million, the Earth is a superheated desert like Venus. Then things start to get really bad.
As the Earth slowly spirals into the sun, a series of events unfolds which unfortunately spells doom for our planet. As the Earth approaches the sun, the atmosphere heats up and blows off, and the oceans boil, basically turning the Earth into a giant comet. But there's worse to come. As the Earth gets closer to the sun's gravity pulls on the near side of the Earth more than it pulls on the far side, and the Earth stretches like putty. At some point, it gets close enough to the sun that the sun's gravity can overwhelm the Earth's gravity, and it shatters, pulverizes our planet.
The Earth is dead, but its ghost could remain, a faint ring of material around the sun. Peter Schultz, planetary impact geologist.
if the Earth or any object gets too close to another object like the sun, eventually the tides will rip it apart. As that happens, it would simply be broken into many small pieces that would then encircle the sun as if it were a ring.
The sun would resemble Saturn with its own faint ring of rocks and dust. A fiery death and a ghostly remnant. If you want to destroy a planet, this could be the way to go.
A great way to destroy the Earth is to drop it into the sun, let it plummet to a fiery death. And we can do this. All you need to do is to pass enough asteroids near the Earth in succession to gravitationally drop it into the sun. And we have that technology. We know how to move asteroids. It's just a matter of getting them on a precise enough orbit to be able to do it.
Maneuvering billion-ton chunks of rock with pinpoint precision at hundreds of miles a minute is quite a stretch. Not to mention the amount of time it would take to capture enough asteroids. We've tried to crush it and burn it. It's time for another plan. An antimatter bomb. Physicists have been searching for over a century for a theory that unites our understanding of the large-scale universe, planets, galaxies, and stars, with what we know of the subatomic world, electrons, protons, and quarks. Their theories are bringing to light some pretty destructive phenomena. One of them could be a world killer. Antimatter. Theorized in the 1920s, detected in the 30s. Now we can create antimatter in modern particle colliders. And the base ingredient for the biggest explosion possible. Antimatter is the most explosive substance ever found. Pound for pound, it's far more powerful than even a hydrogen bomb. But antimatter is hard stuff to find. Everything we see around us, out to the most distant galaxies, is matter, created 13 billion years ago in the Big Bang. It created antimatter too. They look similar. In fact, they are entirely opposite. Put them together, and they wipe each other out. Cosmologist Lawrence Krauss.
Now I have a proton here, and Anti-Krauss over there has an antiproton. And when we bring them together, we're going to make an incredible explosion. Okay, let's annihilate.
This is what happened to all the antimatter created in the Big Bang. It annihilated. If we want to use some for a bomb, we need to make it ourselves. Making antimatter is a bit like firing a gun at a target.
If I shoot a gun at a paper target, the paper that flies out of the target is like matter, and the hole that's left behind is the antimatter. It takes energy to create a matter-antimatter particle pair. In the shooting range analogy, the bullet provided the energy.
In reality, the gun is a particle accelerator, like the one at CERN in Switzerland. Fire protons in a giant tube, steer them around with powerful magnets, use the same magnets to accelerate the protons to near the speed of light, then slam the beam into a block of metal. For every million protons that hit, you get one antiproton. It's as if Plate's handgun only left a hole once in every million shots.
In an accelerator, you only get one particle-antiparticle pair out of every million collisions or so. And so it's really hard to find that one antimatter particle floating around. It's a lot like coming to Niagara Falls and trying to get that one particle out of all the mist. And that's why it's so hard to create antimatter on a large scale.
Assuming we can obtain enough antimatter, the next challenge is to make it into a bomb. Nothing is more unstable than an antimatter bomb. You have to find a way to hold the antimatter without it touching any ordinary matter. If it does, it will explode.
So I have a bunch of antimatter above my hand here. Well, it better not touch my hand, because if it does, poof, okay, at a huge annihilation. But worse, it can't interact with the air around it, because the air is made of matter. And again, you'd get an incredible explosion.
Researchers need a special container to study antimatter. And this is it, a penning trap. Powerful magnets suspend the antimatter in a vacuum.
So if I want to store this antimatter, what I have to do is somehow keep it levitated above my hand, which means I'd have to produce huge magnetic fields in just the right way to keep the charged particles in the antimatter from touching my hand. But I'd also have to store it in an incredibly high vacuum, because any air in the container would again cause an explosion. And so the energies and technology required to produce those magnetic fields, keep that ultra-high vacuum, would mean that you wouldn't have a small object. You'd have to surround it with massive amounts of machinery.
Yet for all that trouble, an antimatter bomb isn't just theory. We can make antimatter, we can capture it, and we can store it. But where do we plant it for maximum effect? If we want to destroy the whole planet, the bomb has to go off near the Earth's core. That's nearly 4,000 miles straight down, further away than London from DC. Right now, that's impossible. The deepest man-made borehole stops at just 7.5 miles. But what if we could? So far, mankind has managed to create a grand total of 20 nanograms of antimatter. That's 100 million times lighter than a dime in your pocket. So the bomb is going to be too small even to see.
Well, 200 feet away in this test range in Arizona, we have the explosive equivalent of TNT. So let's see how big of a bang that makes. Wow.
20 nanograms of antimatter makes quite a blast, but it's way short. To destroy planet Earth, we would need 2.5 trillion tons of the stuff. That's a bomb the size of Mount Everest, at the bottom of a hole 4,000 miles deep. If it were possible, the result would split the Earth into thousands of pieces. With a powerful enough bomb, the pieces would fly out into space and are lost. With a slightly weaker bomb, the pieces fall back under the force of their own gravity, collapsing into a molten ball. an eerie echo of Earth's creation 4.5 billion years ago. It could happen, in theory, but there are a few technical details to iron out first.
So what's the matter with antimatter? Well, if you're trying to destroy the Earth, it'll work, it'll do the job. The problem is you need about the energy that the sun puts out in an entire week. So it's a huge amount, and we just don't have the technology to create that right now.
At the present rate of production, making the bomb would take more than the age of the universe.
The other problem is getting it to the Earth. How do you do that? Well, you'd have to get it to the center of the Earth, and that means digging a hole several miles across and 4,000 miles deep. So in the end, don't think antimatter is probably the most efficient way of destroying the planet.
So, as a way of destroying the Earth, maybe antimatter has some problems. But we know the next approach works, because it already happened once before in Earth's ancient past. Space is a dangerous place. It's full of debris. Rocks the size of pebbles up to rocks near the size of a planet. There are impact craters everywhere, including our moon. These asteroids can hit us as well. An asteroid wiped out the dinosaurs. Maybe a bigger asteroid could destroy the planet entirely. Meteor Crater, Arizona. Almost a mile across, nearly 600 feet deep. Today, science can reconstruct what happened here thousands of years ago. Dr. Dan Durda, planetary scientist.
You wouldn't want to be standing here 50,000 years ago. This iron meteorite, about the size of a small office building or so, it's made out of stainless steel from space. It's about to strike the desert with an impact energy of somewhere between 1 and 10 megatons. And it's that energy that's going to excavate and open up this crater behind me, which is nearly a mile across.
The impact ultimately devastated an area the size of New York City, with 600 times the power of the Hiroshima bomb. And that was small. 65 million years ago, a real monster struck. It was 6 miles across. Sat on the ground, it would outtop Everest by half a mile. The crater was over 100 miles wide. The impact wiped out the dinosaurs and destroyed most of life on Earth. An even bigger space rock could destroy the planet. We're already developing technologies to protect against future impacts. Ironically, you could use those same technologies to make an impact happen. One approach is to hover a space probe near the asteroid. The probe's mass generates a tiny gravitational pull on the rock. Over time, that can change the asteroid's course enough to miss the Earth, or to guarantee a hit. Another protection technology that we could use is a technique called solar sublimation. This diverts an asteroid or comet using nothing more than sunlight. To demonstrate the effect, Durda starts by building a homemade comet.
Some fraction of near-Earth objects are comets, so let's examine what comets are made out of. Let's actually make a comet.
Take some soil, add dry ice, then water, and some chocolate.
We'll put in a few percent of organic material into our comet. And of course, in the outermost solar system, there's a little bit of ammonia here and there. We'll let that be represented by this ammonia cleaner. Let's see if we can pack this up and make ourselves a little comet nucleus.
A magnifying lens completes the apparatus.
If one were to actually focus the light from the sun onto the surface, one could cause some of that water to vaporize away, and just like on this comet nucleus, the jetting action of those evaporating gases act a little bit like little artificial rocket motors attached to the object. And over time, they really do cause it to be pushed slightly off course.
The power of sunlight alone is enough to divert a space rock onto a collision course with Earth. But solar sublimation may not be effective on an object big enough to pulverize our planet. To destroy the Earth, our space missile needs to be big. Like Mars big. We know this for certain because it's happened before. 4.5 billion years ago, a rock the size of Mars struck the Earth a glancing blow. The impact debris created the moon. If it had hit head-on, none of us would be here. We've come here to the vertical gun range at NASA Ames in California for proof. This 12-foot gun fires beads up to 4 miles per second, 6 times faster than a rifle bullet. Professor Peter Schultz, a planetary impact geologist, uses the gun to simulate a Mars-sized object, represented by this small projectile, hitting our planet head-on. The Space Environment Chamber is ready. Schultz makes his final adjustments. But will our scale model Earth break apart completely?
That hurt. That really hurt. Look at this thing, this is worse than a science fiction movie. That's just glorious disaster. There's nothing left.
A head-on strike, destruction guaranteed.
So the things that destroy an object is going to be a combination of the size of the object, the speed of the object, and the angle. The lower the angle, the less likely it'll completely bust it apart. So to really destroy the Earth, you need something that's humongous and needs to hit straight on.
Now we know what it takes to use an impact to destroy planet Earth. Asteroids and comets are just too small. We need to move something the size of a planet onto a collision course. That's a level of technology we won't be reaching anytime soon.
Now, we can move asteroids around and we can move comets around, but those are only a few miles across. The problem here is that we need something really big. Mars is about 1/3 of the size of the Earth, and even that hitting the Earth won't destroy it. We would need something almost as big as the Earth itself, something like Venus. And even then, we just don't have the technology to be able to move something that big with that kind of precision to aim it at the Earth and blow it up.
Destroying the Earth with a space rock just isn't gonna happen. Perhaps the killer punch won't come from space, but from right here on Earth. Genetics, robotics, nanotechnology. Researchers hope machines will lead us to a brave new world. Already, robots can learn, build other robots, and cooperate with each other. It could be the beginning of a new age. It could also be the beginning of the end. Right now, we can only build robots that work with humans in control, but science is working towards machines that can think for themselves and even reproduce. Robots that can make copies of themselves without human control could one day take over the world. Hod Lipson, professor of robotics. Lipson is a pioneer in robot replication.
If this robot could make another robot identical to itself, and then those two robots can make 4 robots and so forth, these robots could fill up a space such as this here fairly quickly.
Once the first replicate is made, there's no stopping the process. But first, we've got to make them. At Cornell's robotics lab, Lipson and his team already make robots that learn, robots that build, and robots that build themselves. This is the world's first self-replicating robot. Supply it with building blocks and it assembles them to make a copy of itself. It needs Lipson and his lab techs to keep it stocked with plastic cubes. So this robot is pretty benign. To destroy the Earth, we need to develop robots that use smaller blocks and eventually individual atoms.
We've been trying to make robots made of much tinier cubes on the order of 0.5 millimeter, and you can barely see them. There's about 10 of them in this container here. We're trying to get these very small units to combine together, and the smaller they get, the faster and more easy it is to replicate.
Lipson thinks that advances in robotics will revolutionize design and manufacture. But where there's progress, there's also danger. In theory, nano-sized machines could start to replicate out of control. Self-replicating nanomachines could, in theory, destroy all life on Earth. To destroy the planet itself, we need something more. To reproduce, a robot needs energy and raw materials. In other words, food. The more food there is, the more copies our robots can make. And the biggest source of food on the planet is the planet itself.
The ultimate kind of self-replicating process is something that's inspired by nature. So if we can have a machine that can essentially self-replicate using resources in the environment, food and energy, then that would be a pretty big achievement.
And the biggest natural resource on Earth is rock. Design a self-replicating robot that feeds on rock, and it has 6 trillion tons of food right under its feet. Some living creatures already use rock. Rock-feeding bacteria live in the Earth's crust, even several miles deep. But nature's rock eaters are good for the planet. They help form soil and keep life ticking.
There's a whole suite of rock-eating bacteria that we've now uncovered on the Earth, which will go and chew up and eat and use the materials in the rocks for their sources of energy and for the sources of compounds they use to build other biologic molecules. There are literally biologic organisms that do just this, eat rock.
Rock-eating, self-replicating robots. But they've got to be smart. They need to cooperate. Professor Alan Winfield, roboticist in charge of the Symbrian project, to design robots that swarm like insects.
Symbrian is a 5-year project to try and build a swarm of self-assembling robots. Perhaps as many as 30 or 40 will physically join and then behave and act as a single organism. The big challenge is going to be how to get the robots to first of all decide what to be: a foot bot, or a knee bot, or a sensor bot, or a brain bot, and then work cooperatively so that, for instance, the organism can stand up and walk.
We can already make robots that reproduce. We can make robots that cooperate. Put them together, and at last we may have our planet killer. Here's the math. Say each robot takes 1 day to replicate. Then after a single month, you have over 1 billion robots. After a year, you have trillions. Earth is covered with machines that do nothing but gobble rock. In the end, no more rock, just a huge ball of self-replicating machines.
Now, what are robots made of? Well, iron, magnesium, aluminum, and silicon. The same thing the Earth is made of. And so all you have to do is create one of these self-replicating robots and let it out into the wild. It'll make a zillion copies of itself, and they will consume the Earth, and eventually there'll be nothing left.
Success at last? Perhaps not. In our quest to destroy the planet, we've tried devouring it, incinerating it, pulverizing it, blowing it up, and breaking it down. Planet Earth is a proven survivor. It has taken everything the universe can throw at it for 4.5 billion years. And one thing is certain: we're still here.